Welcome to the workshop on renewable energy technologies and resilient generation capacity for microgrids. We have more than 100 participants registered, which demonstrates the high level of interest in the rapidly developing field of microgrid design, power generation, planning and implementation. Microgrids are nothing new, but recent technological advances in small-scale renewable power generation and smart grid design make them a cost-effective solution, particularly for places where large-scale transmission either does not reach or fails to give a reliable supply. Universal access to affordable, modern, clean energy is Goal 7 of the UN Sustainable Development Goals. The SDGs state that energy is central to nearly every major challenge and opportunity the world faces today, be it for jobs, security, climate change, food production, or increasing incomes. Access to energy for all is essential. In sub-Saharan Africa, more than 625 million people have no access to modern energy services. Most African countries, 42 in all, are net energy importers, and fossil fuel-fired plants account for 81% of total electricity generation, which is mostly in South Africa. Most large infrastructure projects are public investments financed by national budgets. The estimated cost of bringing Africa's energy infrastructure to modern standards is $93 billion USD a year. There's a huge gap between energy supply and demand in Africa and other developing countries that successive efforts have failed to bridge. The envisaged holistic hybrid microgrids will lead to a prototype model for the creation of sustainable and resilient distribution networks for off-grid locations, with the potential to enable the electrification of millions of households. Typically, the electricity distribution system planning and real-time system operation are considered as two separate stages in the overall grid design. First, information such as consumer load profiles and growth, land developments, available generation units, the regulatory framework, and weather conditions are used in the planning phase to design the distribution grid for the worst-case scenario. In the second phase, the real-time operation strategies are designed to optimize the grid operation and reduce the operational cost. This approach is appropriate for regions with a developed, strong electrical distribution infrastructure and standardized ancillary services and market-based energy trading mechanisms. However, it may result in prohibitive high costs and suboptimal energy system design and operation in developing countries with weak or no electrical infrastructure, because the requirements of remote rural communities in terms of demand, flexibility, power quality, reliability, robustness, maintainability, cost, resource access, and local acceptance differ substantially from those in developed countries. In addition, the lack of existing electrical infrastructure diminishes the available data required for the planning phase, such as load consumption patterns and types of generators and costs, and so on. Finally, the existing pool of energy generation units is restricted by the scarcity of resources and the technical expertise of the local communities. Therefore, a power system design in developing countries enabling self-sustained and resilient energy distribution should ideally take a holistic system approach, integrating both the planning and real-time operational design into a single joint design stage. Such an approach should explore the socioeconomic and energy resource dimensions to extract energy consumption and generation relevant data and incorporate them through the appropriate cost factors and constraints in the overall optimization-based design procedure. This workshop is part of a 3-year project on creating resilient sustainable microgrids, funded by the UK Engineering and Physical Sciences Research Council through the Global Challenges Research Fund. The project is composed of 3 work packages. The first on planning and design of flexible and robust microgrids. The second is on tailoring the microgrids to community needs, and the third on sustainable and resilient energy generation. Last week, we held a well-attended workshop exploring the electrical engineering perspective of microgrids. Today's workshop is from the third work package on generation and is focused around three themes. Firstly, opportunities for renewable energy technologies in developing nations. Secondly, sustainable generation activities in our project, CRESUM HYRES. Thirdly, case studies on renewable energy generation for rural development. The workshop starts with a plenary session by the eminent chemical engineer, Prof. J.B. Joshi from ICT Mumbai, focusing on the opportunities for renewable energy generation in India. Topics covered in the workshop will include opportunities for using bioenergy, solar PV and solar thermal, as well as hybrid renewable energy technologies, assessment of available resources, and simulation of proposed solutions. I will now hand over to Dr. Andy Ross to chair the first session.
So thank you, John, for that introduction. And it sets the scene very well for this workshop and how it links to the other workshops that we have in this series. Just before we start and we introduce the agenda and move into our first sessions, we'd just like to give you a little bit more introduction into the CRESUM HYRES project and a little bit more introduction into the structure of the different work packages. So I'd like to welcome now Dr. James Hammerton, who is one of the senior researchers on the CRESUM HYRES project, to give a short introduction to put the project into context.
Great, thank you very much, Andy. So yeah, my name is James Hammerton, and I'll be just giving a quick overview of the structure of the CRESUM HYRES project. So I think firstly, to start off, I should say what CRESUM HYRES is. So this stands for Creating Resilient Sustainable Microgrids Through Hybrid Renewable Energy Systems. So as John alluded to in the introductory section, this is the research we're showing you all today is part of a much wider project. So what we're presenting today is work package 3, and this is all about sustainable and resilient energy generation. And I think the resilient aspect is so important because we see many microgrids around the world having many technical issues with their generation technology. So the tasks we're looking at are things like the sustainable resource assessment. We've been looking at different conversion options of biomass, whether this be through solar thermal processes, or biological processes. Another really important aspect of this project is we're looking at engine generators. Now, obviously, engine generators are available throughout the world. The real issue, I think, for microgrids is just the cost of diesel. And this is especially high in certain countries in sub-Saharan Africa. So really, they provide great flexibility, but we really are interested in different fuels. So hopefully some of you saw the conference, the workshop last week, and this is on work package 1, and this is all about planning microgrids. And the real sort of the main output of work package 1 is to create a planning tool that's free to use, something that is in competition with Homer, which is I guess the industry standard microgrid planning tool, but it also has many limitations. And one of those huge limitations is the fact that people have to pay to have a license. So if you're interested in planning tools, stay tuned in the future months, and we're going to be having versions of this software coming out and freely available for any researchers to use. So how we're sort of plugging into this is we're providing some of the data from our resource assessments, and we're looking at the different conversion options and the costs, and that's going to feed into this work package, and it's going to give a strong indication of what the costs are of using these different technologies. So there's the second work package 2, which is led by Jon Lovett, is all about the socio-economic aspects of microgrid planning. And there is a conference on this workshop next Thursday. So hopefully, if you're interested more, hopefully you'll be able to attend. So we've been looking in various sub-Saharan African countries, and we've been doing some really interesting willingness to pay surveys, and we're using a choice card experiment, which gives it a better idea about how much people are willing to pay for hours of use of electricity, the reliability of electricity, and what appliances they can use on the grid. So it's really giving a really great idea of how much people are willing to pay, and how that changes in terms of other sort of factors in the community, such as the family household income. So as part of this project, we've been looking at various case studies. So in Africa, we're focusing on 3 countries that we've already got really strong partners in, and you'll be hearing from some of them today. So we're looking at the Republic of Congo, Tanzania, and Uganda. So we're really interested in these countries because of the lack of electricity access in these countries, and often grid connections are not feasible. One of the really interesting case studies that we visited in Uganda is there are a set of islands in Lake Victoria. There's Kalangala Island, which is the main one, and they've recently installed a mini grid there, and this is a solar PV, battery and diesel generator system, and that's been operating for some years now. And what's been really interesting going there is to see what kind of technical problems they have, what kind of issues they have with demand, and it's interesting to start thinking about how we can move away from using diesel, which is one of the biggest costs in the power station, and potentially what kind of bioenergy alternatives there would be in this case. Another area we're looking at is across the other side of the world, and we're looking at the island of Sumba in Indonesia with our partners at the Resilience Development Initiative based in Indonesia itself. So we often think of Indonesia as being more developed than many of the sub-Saharan African countries, but there's really a west and east divide. So the islands in the west tend to have very good energy access, and the people are comparatively wealthy, but in the east the islands are much poorer. So we're looking at Sumba because it's in this east. It's in the region of East Nusa Tenggara, and the wealth of these communities is similar to sub-Saharan Africa. What's really interesting about Sumba Island is it's a real tourist location for some of the really wealthiest people in the world. A lot of footballers go there for their holidays, but it's overall quite a poor area, and it's known for these distinctive houses that we've got pictures here with these thatched roofs that go up to a central spike. So there's been a lot of previous work in Sumba Island. There's been this Iconic Islands initiative to look at moving Sumba Island over to 100% renewable energy. So there's many examples of different microgrids there. There's pretty much every technology you can think of being used in a microgrid. There are micro wind turbine microgrids, there are micro hydro mini grids, and there's also plenty of solar PV mini grids. So just to save the date, I would like to ask you to go to the Eventbrite website for the work package 2 conference, which is on the 17th of September, which will be starting at 8:30 British Summer Time. If you want to find out a little bit more about the socioeconomic needs and how we're looking to investigate those in terms of microgrids. So that's the end of my presentation, and I'll pass you back over to Andrew Ross.
So thank you, James. If we could just put up the presentation with the introduction and the agenda, and I'll just run through the agenda quickly before we move on to our main plenary session. So as James said, this is the second workshop that's been organised by CRESUM HYRES with the focus on generation. So next slide, please, James. And it will focus on these 3 main themes. So the opportunities for renewable energy technologies in developing countries, the sustainable generation activities from the CRESUM HYRES project. So there'll be some dissemination from the project today. And then a series of case studies on different renewable energy generation technologies. So we've structured the agenda to address these. So firstly, we have a plenary session from Professor J.B. Joshi, which is going to have a focus on leveraging bioenergy resources for developing the rural Indian economy. We're then going to move on to 2 technical sessions. So the first one is on sustainable generation. Again, we have a keynote speaker in this session from Dr. Dalvi from ICT Mumbai. And then we have a series of presentations from academics from the University of Leeds. We have Dr. Rolf Crook, Dr. Valerie Dupont, Dr. James Hammerton, you've just heard from, Dr. Hugh Lee, and also Nina Ortiz, one of our PhD students. We'll then move on to a second technical session, which is focused really more on case studies. So we will have a presentation from Dr. Mary Susan Abo, one of our partners from Creek in Uganda. We'll then have a case study presentation on gasification from Opio Miria at Creek in Uganda. We'll then have another case study on the utilisation of sweet sorghum in Nigeria by one of our PhD students, Francis, from University of Leeds. And then there'll be a presentation from myself on anaerobic digestion. So at the end of each of these technical sessions, we will have an opportunity to discuss some of the work. And some kind of just basic rules of the meeting is that if you could please, if you have questions, if you could please put them into the chat, and we will be monitoring the chat and picking out those questions, and the chair of the sessions will then put those to the presenters at the end of each of the sessions. So if you could please keep your microphones off if you're not speaking and your videos off. And then hopefully the meeting will run smoothly. So that's the introduction. So now it gives me great pleasure to move on to introducing the plenary session and chairing the plenary session. I would like to introduce Professor J.B. Joshi, who is currently the Emeritus Professor of Eminence at the Institute of Chemical Technology in Mumbai. And he is the president of the Marathi Science Congress. He has an extremely long and distinguished career in chemical engineering, spanning several decades. He has guided many doctoral students and many master's theses, and he's published more than 500 papers. And his recommendations and his work as a chemical engineer has led to huge amounts of improvement in chemical operations. This has resulted in huge enhancements of business opportunities within the chemical engineering sector. So it's not surprising that Professor Joshi is actually India's most sought after chemical engineering consultant. So despite all of this work, Professor Joshi still teaches a course on multi-phase reaction engineering to undergraduates at ICT in Mumbai. He is renowned for being a fantastic lecturer and has a real passion for education. So we are very, very honoured that he has agreed to talk to us today on the leveraging of bioenergy resources for developing the rural Indian economy. So it gives me great pleasure to introduce Professor Joshi, and we will now hand over to you, Professor, to give us an introduction and your thoughts on this subject.
Thank you, Professor Ross, for nice introduction. First of all, I give my plenty compliments to the organizers for organizing a workshop on very important subject, and thank you for giving me this opportunity. As mentioned earlier, I'll be talking on leveraging bioresources for developing the Indian rural economy. I have about 3 case studies which I will explain to you. So next slide, please. The total land area is about 329 million hectares, and the map of India has been superimposed on Europe. So right from Ireland up to Belarus, and from the north, right from Norway up to the south of Italy, that is the sort of area that India occupies. EU area is 448 million, so it is about 75%. Arable area is 160 million hectares, second largest in the world after US, and irrigated area is 83 million hectares, which is largest in the world. Next slide. If we see the productivity of India per unit hectare, and I have mentioned here large number of agricultural products like onions and mangoes and vegetables and sugar cane. The productivity of India is approximately 2 times less than the whatever is maximum achievable. In many other cases, it is even less than that. In other words, the productivity of the land in terms of the land has not remained fertile. So we have analyzed for a particular crop, and we have taken soybean as a crop as a reference. And for soybean, we have carried out the soil analysis and what is the meaning of fertile land and unfertile land. And we get the analysis components and we get the difference between the two. And I'm going to explain this later, how to increase the productivity by injecting whatever is not there in unfertile land in order to make fertile and increase the productivity at par with whatever is maximum proven in the world. Next slide. The first point I'm going to explain is the conversion of biomass. I'm going to tell you how much biomass is available in India. It is 600 million tons, out of which approximately 250 million tons is consumed by cattle, and about 350 million tons of agricultural biomass is available. And then there are several technologies which we are looking at. One class of technologies is biotechnology, and the other class is the thermal conversions. So we have worked in all these directions. This is very well known that biotechnology on one hand can give 2G ethanol, or it can give value-added products, or on the other direction, the anaerobic biological treatment can give methane. Here we have worked substantially, and there is in the next slide, it's showing the plant together with bio-CNG as a vending machine. We can go to the next slide. So you can see the vending machine, and in the background you can see there is a anaerobic digester followed by a purification from H2S and pressure swing adsorption for CO2, and we get more than 97% biomethane, and 3-wheelers and 4-wheelers and 8-wheelers are being that is energized with the help of this biomethane. We are scaling it up further to about 1 million liter the anaerobic digester. The next slide. Now, if I talk about the economics of this, if we pay 3 cents per kilogram for biomass to the farmers, and whatever is their productivity, and if we take either rice or wheat as a product, the 3 cents per kilogram, they fetch comparable money as comparable to either wheat or rice. So this is a good price. And 8 kilograms of biomass gives 1 liter of alcohol, which is about 0.5 pounds per liter. That is the price in India. And the biomass required is 8 kilograms, that will cost about 24 pence. But we get about 4 kilograms of fertilizer, which can be also sold at 3 pence a kilogram. So the net raw material cost is about 12 pence per liter of alcohol. If we add to this the cost of purification and cost of compression and cost of other utilities, the cost of production comes out to be about 26 to 27 pence for a liter. And as I told you earlier, the price of bioethanol in India is 0.5 pounds. So there is a margin. However, if we calculate the depreciation and interest, then that works out to be from 0.26, it becomes 0.4 pounds. So there are many opportunities here to reduce the capital cost, and it is my belief that we can reduce the capital cost at least by 40%, and work is going in that direction. The other biotechnological route is 2G ethanol, and a lot of work has been done in our institute. And in the next slide, it shows the pilot plant of treating about 10 tons per day of biomass. It has been a successful technology, but here also we feel that there are huge opportunities in terms of reducing the capital cost, again by about 40 to 50%, so that it will become competitive as compared to other resources of ethanol. Next slide. Here I'm going to talk a little more. You will be surprised that 30% of energy in India is used in household cooking. And for most of the household cooking, the agricultural biomass is used. And the number of families who are using biomass-based cook stoves are 180 million. And the current thermal efficiency is about 12%. The reason I'll tell you within a minute. And improved efficiency is possible. I have written 40%. If we prove 40%, then the nation saves about 8 billion US dollars. It's a huge money for India, but we have been able to go up to 50%, and we have seen the opportunities for taking it up to even 60%. So that $8 billion is expected to become $16 billion. This entire story I will narrate in a short time. Next slide. This is why the efficiency is 12%. This is a typical cook stove, and biomass is introduced, and air is through that hollow pipe, and you can see the lot of soot is there, which is irritating the eyes. In addition to soot, there is carbon monoxide and some hydrocarbons, and a lot of pollution happens. These types of cook stoves are also used in Africa, and about 1.6 million women in kitchen and young children, they die every year because of the pollution generated by the cook stoves. So therefore, we thought we should address these problems. And next slide. There are similar problems in the internal combustion engine. I have exaggerated this picture, though the picture is real, but this is not common for all the vehicles. The point I wanted to show was how the efficiency is improved by analyzing and what is the method of analysis. So we have used exactly the same method as that of internal combustion engine. This mileage is 5 kilometers per liter, and how it has been improved. The next slide, please. So this is an example where Princeton University, with the help of national laboratories, SNL and LNL, and with collaboration with industry, that is General Motors and Ford and Chrysler, they tried to understand what exactly are the problems, because the efficiency of internal combustion engines, when they started the research, was about 25%. And they identified the problems which are written on the extreme right side, that is flame quenching and soot kinetics and complex composition of gasoline and diesel, flow through intake and exhaust ports, influence of fuel variability, and knocking. These were the problems. And therefore, the next slide, a detailed computational fluid dynamics was done in terms of the sprays and drop size distribution, and what happens at every point in the internal combustion engine. That was analyzed, whether all the points are efficient or some points are idle, and they are not doing the job. So here what is shown is the starting efficiency is 25%, and the inefficiency of 75% is divided into 3 portions, the 5% and 20%. Some goes to the cooling system, some goes to the exhaust. And how by systematic efforts by these 3 agencies put together has reduced the losses. And in the first attempt, the 25% efficiency has been improved to 33%, and from 33% to 44%. And some time back, I visited Princeton, and now they have placed that we are going to enhance this 44% to 60% efficiency. What I'm trying to emphasize here is understanding the entire flow patterns through computational fluid dynamics, and coupling of computational fluid dynamics with all the possible reactions which are happening, and trying to understand the efficiency of each point in the internal combustion engine. That has improved, and that has also shown the opportunities that how we should improve the efficiency of internal combustion engine to 60%. Now, I started with an example of a biomass-based cook stove where the starting efficiency was 12%. The next slide. Here I have shown, that is, I had organized about 25 workshops in rural India, we academicians, we need to be close to the users while understanding the real problems. Many times what happens that we imagine that these are the problems and we solve, and many times there is a difference between what we do research in universities and what is the need of either industry or society. At least these are my observations in India. Therefore, what I try to do in all the cases, let it be industrial practice or societal practice, but I hold at least 20 workshops in understanding the problem. Because improved cook stoves, this problem is not new. It has been there existing for 50 years. And in all these workshops, what I discuss with these housewives is why they do not use the improved cook stoves which are available in the market. And I collect their problems, which I convert into science, but the methodology used is exactly the same. Try to understand computational fluid dynamics, try to understand the reactions which are happening, and make every point in the cook stove more and more efficient. So therefore, the next slide, here you can see the cook stove has pallets. The red cylinder that you see is a conducting ceramic cylinder, and the blue cylinder is a non-conducting ceramic cylinder. And both of them have been fabricated by the students of my institute, and they have received innovation awards. The most important part was it was to be accommodated, both the cylinders put together in 1 pound to be made, and they have been able to make. So in such a complex geometry, where air is blown inside with the help of a small the battery-based blower, and the air distribution occurs throughout the cook stove, and the computational fluid dynamics was done. As we know, the fuel burning passes through 3 steps. One is the drying and moisture removal. Second is devolatilization, where most of the energy is available. And finally, the burning of the char. So all these reactions were included in computational fluid dynamics. We could analyze all these components in controlled experiments and the reactions, say methane combustion that is available, but we carried out detailed analysis with respect to time and modeled the entire cook stove. Next slide. These are some of the temperature profiles that we get from computational fluid dynamics. And like internal combustion engine, we slowly improved from 12% to 26%. Next slide. And here you can see the extreme right is LPG based cook stove, where we have a blue flame, and this is the cook stove. The C1 is biomass based, and which is also giving exactly the blue flame, having temperature of about 1080. Earlier cook stoves, they give a temperature of 500 degrees and yellow flame. And of course, therefore, there are many uncombusted things and which are also polluting. The C cook stove, which I had shown schematically earlier, we have increased from 12% to 26% to 28 to 32%. But right now we are getting 50% efficiency. And after removing 50% efficiency, if this cook stove has to work for 1 hour, then this blue flame we are getting only for 30 minutes. So this means there are still opportunities to improve further. And now we have taken a task to improve that efficiency from about 50% to 60%. So whatever the savings I mentioned to you earlier, the savings will become double, because I had assumed only 40% as the end efficiency we have already received. So approximately 1 million cook stoves have been sold with a price of about in the range of 5 to 7 pounds per cook stove, and everything is accommodated within that, including profits. Next slide. These are those conducting and non-conducting cylinders. In most of the research, we collaborate. Now here in Mumbai city, there is another institute called Indian Institute of Technology, and there is a material science department, and we collaborated with Professor Bhargav, and our students did that hard work and developed this conducting. So non-conducting means even the temperature inside is 700 degrees, outside temperature is only 50 degrees. So that is the kind of conductivity they have been able to. This is a subject of a separate lecture. So going to the next slide. This is the biomass which is available in India from the variety of crops, rice, wheat, sorghum. And at the end, you can see that approximately 300 million tons of crop residue is available just now. So how to valorize this crop residue? One outlet I mentioned was making biomethane. Another outlet I mentioned to you was the cook stove improvement. The third one was bioethanol. But now I'm going to focus most of my lecture on the technology of pyrolysis. Next slide. So here, when we do biomass pyrolysis, that is heat the biomass in absence of air, we get gaseous product in which we have mostly carbon monoxide, carbon dioxide, methane, ethane, butane, butene, isobutylene, isobutene. So all these products are there. And then the liquid products are there, which can be used for transport fuels, or there are many, many valuable chemicals in the liquid that can be also a separate subject, and we get syngas. The solid, which is char, that I want to emphasize a little bit. Char as a use of catalyst or adsorbent, that use in industry, there is a use, but the consumption may be not more than 5% of what is the char possibility or availability by pyrolysis. And major use we are considering in soil amendment. So I described a little bit the difference between fertile land and unfertile land. There are 22 inorganic parameters. There are 4 or 5 organic parameters. Most of it is organic carbon. And then there are 16 microbiological parameters. So if we analyze the soil, we come to know what exactly is wanting. So we take a char and give the property of ion exchange, give the property of porosity and adsorptivity, and whatever is the difference between the fertile and unfertile land, all those inorganic, organic, and microbiological properties we inject into the char, and we have studied in great detail the productivity, enhancement in the productivity of soybean. Next slide. So this is how we measure the kinetics of pyrolysis. We use TGA, we use a drop tube apparatus, we use rotary kiln, and then we have a pilot plant of one is 5 kgs per hour, that is approximately 100 to 120 kgs per day. And we have another pilot plant of 1 ton per day. So we measure kinetics of pyrolysis and try to validate it. We have a recent progress, that is the analysis of the raw material and the kinetic parameters. We have studied plenty biomasses, and the proximate analysis and ultimate analysis, and whether there is a direct relationship between the final end kinetics and the analysis of biomass. Next slide. So here I'm saying how this technology of pyrolysis is going to the village India. There are plenty villages, and here I'm considering a cooperative basis model, a business model. And I say that let us make a cluster of 5 villages. The average population of 5 villages is about 25,000, and they hold about 5,000 hectares. The existing extra biomass available with such a cluster is about 12,000 tons. Now, if we use the strategy that I have told for soybean, that is increase in productivity, we have been able to get, depending upon the initial fertility, if the initial land is fertile, then we did not get any increase in productivity. That is obvious. But if we start from unfertile land, then we have been able to increase the productivity by up to 76%. And in some cases, even 300%. But the Indian condition is, as far as oil seed, that is soybean, is concerned, we still want soybean and we are importing, therefore increasing productivity is required. But if we see other pulses or rice or wheat, we are already self-sufficient. So increasing productivity by 50% or 76% is not going to help the nation. And therefore, the model that we are proposing, that increase the productivity by 50% and free the land by about 33% land is remaining free, and grow only energy crops. As all of us know, the photosynthesis efficiency is pretty low. When we say the productivity is 10 tons per hectare per year, then the photosynthesis efficiency is only 0.3%. And there are some grasses like bamboo, where we have done a lot of research, and we have been able to get about 3% photosynthesis efficiency, and we are looking forward to 4.5% efficiency. So the model is increase the productivity by 50%, make 1/3 land available for energy crop, where photosynthesis efficiency is much better than whatever is usually available. So the next slide, what I consider is, now that extra biomass which is available, we give that price, that benefit again at 3 pence a kilogram, and that is a lot of money, 3 pence a kilogram, and they produce more than 100 tons per hectare. That is a good money for them, which is more than what they produce through rice and wheat. So land available is 1,600 hectares, that is 1/3 of, and by pyrolysis, the bio oil we get is 64,000 tons, and biochar is 48,000 tons. I have taken oil at $0.2 US per kg and 0.03, that is 3 cents per kilogram of biomass. And that is sufficient for improving the productivity of land. The next slide. So what are the benefits to India? If we take bamboo as a and take 1 year as the basis, the biomass value to the farmers is 4.8 million to the cluster of 5 villages. The number of pyrolyzers required are 10, and the capital cost return is about 15 million. The depreciation and interest of the capital cost is 3 million. Operating cost is 0.8 million. This manpower which is required is 500, and the salary is 1.2 million, which is very attractive in India. And here I want to emphasize that we are not only solving the problem, but we are creating opportunities for jobs. And these job opportunities are 500 per cluster. So the total expenditure is 9.8 million, and gross profit is 4.44 million. So in addition to what they get for biomass 3 pence per kilogram, this profit is also of the villagers in those 5 villages. Next slide. So if this technology or business model is implemented throughout the nation, per cluster, I have already said there are 500 jobs. and 1.2 million get distributed among 500 people. Biomass advantage to farmers is 4.8 million. That is equivalent to the main crop. Extra per capita income is about $417. Please note that the average per capita income of India is $1,600 per person per year. And that is average of the nation. But average of the villagers is in the range of $600 to $800 per person per year. So this $417 extra income by pyrolysis, it is very, very attractive. It is between 50 to 70% of otherwise the per capita income. The energy produced per cluster is 50,000 tons of oil equivalent. This oil from pyrolysis does not have the calorific value same as the good quality oil. So we get about 50,000 tons. So energy produced in 200 million hectares, that is from India, is about 2,000 million tons of oil equivalent. And I want to emphasize here that the current consumption of energy in all the forms, let it be solid, liquid, electricity, biomass, all put together is 700 million tons oil equivalent. And we are considering that if this pyrolysis technology is implemented over a period of next 10 years, the 2,000 million tons of oil equivalent will be the energy consumption by 2035, and we will be ready in terms of energy resources. Next slide. So let me come to the conclusions. India has tremendous bioresource potential, and it can be enhanced further. Leveraging this potential can generate huge wealth, and wealth will be generated at the grassroots, and millions of rural jobs will be available, and potential to transform the rural Indian landscape. If we say 500 per cluster, it means that we are going to create 20 million jobs for India. And here I conclude, and I again thank the organizers for giving me this opportunity. Thank you very much.
Thank you very much, Professor Joshi, for that fascinating introduction into the opportunities in India. It was very, very interesting. I would like to invite anyone who has a question to put it into the chat. We have a few minutes where we can have a short discussion with Professor Joshi. I'm sure if we don't get through all of these questions, we can maybe send them to him at a later stage. However, I'd just like to raise a few questions, Professor Joshi, in the absence of others, just to get things started. It's very interesting, pyrolysis as a technology. And of course, it produces this pyrolysis oil, which could potentially can be upgraded into different fuels. I was wondering, what would be, in your opinion, the best types of upgrading strategies for converting pyrolysis oil into a usable fuel, perhaps that you could use in a generator? What do you see as being, if you like, the downstream challenges for realizing pyrolysis as a game-changing technology?
Yeah. My first strategy, which I have been implementing, the gaseous products, as I mentioned to you, has hydrogen, methane, ethane, and C3, C4 fractions. So when we recycle this completely, and some of it is anyway required for burning because it is an endothermic reaction. But if we call this as hydropyrolysis, because some of the products containing much more hydrogen, methane has 4 hydrogens, whatever we wish to call, but if we recycle this, then we get very high value products. I have observed that in some of the pyrolysis, we get more than 30% BTX when we carry out this hydropyrolysis, and many valuable chemicals like glycol and many high value alcohols and acids we get. So this is one direction which we are pursuing, that is the pyrolysis itself carry out under different conditions. The second is, of course, the hydrotreating. That is as we know, all the biomasses are carbon, hydrogen, oxygen compounds, and in the fuel we don't want oxygen. And in the pyrolysis we knock out oxygen either by reacting with hydrogen and or by reacting with carbon. So we make CO2 or water. If it is with hydrogen, then C by H ratio is high and we get solid product. If it is with carbon, then H by C ratio is high and we get the liquid product. And we are getting both the products here. But we are unable to knock out all the oxygen by pyrolysis. And therefore, some kind of hydrotreating is required in order to knock out all the oxygen. But my first recommendation is change the parameters of pyrolysis and try to get it as a feedstock for chemical industry. And I believe that not all the problems will be solved, but it will become a major component as far as the feedstock for chemical industry is concerned. And one should focus more on that. And obviously, if we are considering nationwide biomass getting converted into pyrolysis, then as we know, hydrocarbons required for energy is approximately 10 times whatever is feedstock required for chemical industry. So we may get much more in pyrolysis than for feedstock for chemical industry, and we should develop technology, something like hydrotreating or hydroforming, in order to knock out the remaining oxygen and try to get hydrocarbons. Thank you.
Yeah, thank you, Professor Joshi. There's a couple of comments come up in the chat. One is regarding the kind of the business development of pyrolysis. How is it you know, is pyrolysis on a small scale, or is industry interested in investing in this, and how does this compare to, say, other technologies for the production of things like biodiesel? So there's a few comments. There's another comment come up, which I'll ask you now, and then you can maybe address this one too. This was regarding the development of the cook stove, and of course it looks fantastic. You have this fantastic blue flame, very efficient, clean burning stove. But what are the challenges for actually people, you know, using these stoves? Why are people perhaps not using them more? Is it a cost issue? Are there other issues associated with uptake?
Yeah. Now, as far as pyrolysis is concerned, we have been able to scale up to 50 tons per day. And there are more than 20 plants in operation right now. In some cases, it is a plastic waste in some of those cases. And therefore, one plant in London is operating using our technology, but it is a plastic waste. But the machinery is the same, technology is the same, gas, liquid, solid products are the same. Only thing is we get a lot of liquid product when we start from plastic waste, some quantity of gases. And there also we have been able to recycle the product gases, which is hydrogen, methane, etc., and try to get very high value products like BTX, etc., from the pyrolysis of plastic. So it has been scaled up to 50 tons per day and operating at more than 20 locations and throughout the world. As far as cook stoves are concerned, whenever I develop a technology for the society, I'm a faculty member. I have been a faculty member in the university, and trying to understand the mindset of society, this was a new subject for me. That is why people don't use any innovation which happens in the university. So first thing first, the university people have not made friendship with the society. They don't come together and then don't eat together and then don't move together. They don't dance together, which I have started dancing with them. And this is first thing. Second thing is the societal mindset. We natural science people, chemistry, physics, biology, chemical engineering, mechanical engineering, we are not capable of understanding the societal dynamics. And therefore, I take my friends from social sciences department and they understand the social mindsets and how to change the mindset. According to them, that is a science, how to change the mindset. So I take a lot of help. I respect them. Actually, the way in which they come out with solutions to the problem of mindsets is enormous. I'm ready to give another lecture on social mindsets and what is that these social sciences professors they try to do, but they are capable of doing. Actually, I get surprised. One set of these professors, there was a huge drinking habit, alcohol drinking habit in one part of the society, and they worked and they changed the mindset of those local people, and the drinking habit has been reduced to a substantial extent. So I take help of these people, and whatever new technologies for the society are to be done, changing the mindset is important, but mixing with them, I need to mix with them as if I'm not an outsider, I'm not a giver, and they are not a taker. We are benefited, and I must tell very, very frankly to this international community that I learn a lot of wisdom from these village people. So there is a give and take, and this is where I'm able to implement.
Thank you, Professor Joshi. That's fantastic insight. There are a couple of other little questions here and there which people have asked, but we are now approaching the end of our session. There was just one question that someone raised, which I thought was interesting and worth asking, and that was, what do you think is the greatest barrier for these technologies developing, or what would you say was the biggest blocker, if you like, for these technologies developing?
See, in my opinion, for research, very little is required. What is required is excellent ambience. All the sophisticated equipment, the library, the internet, all these are useful, but these are not very mandatory. The dedicated students are plenty if they are given the challenging jobs, and if they are helped whenever they face any genuine difficulty. In most of the cases, my students, I permit them to solve the problems on their own. So the first and foremost is to generate confidence in the university sector that we can solve the societal jobs. This is one. The second, very important, and I consider it to be most important, is to be with the society or with the industry, be with them and try to understand what exactly the problems they are facing because of which they are not implementing technology. We in university somehow try to remain within the university and we publish a lot, but the starting point of publication is perhaps earlier publication. It is not our own observations in industry and society. What exactly is the need of the society, need of the industry? And if the beginning of the research, I consider that as the most important point while doing research. And of course, I emphasized earlier, changing the mindsets of industry people and societal people is also very, very important. A lot of patience and perseverance is required by the university faculty, but that is mandatory if you want to succeed.
Yeah, that was very wise words, Professor Joshi. Thank you for that insight. Well, I'd first of all just like to thank you for agreeing to give us this insight today. It's been a fantastic presentation. Thank you very much. We would welcome you to stay and make any comments later on in the presentations. And if there are any other specific questions, then perhaps I can email them to you if people are really keen. But again, I would on behalf of everyone, all of the presenters, the organisers, and the delegates, I'd like to thank you for your presentation. So some virtual clapping.
Thank you for the opportunity. Many thanks.
So I think now we can move on to the next session in our in our workshop, which is moving into technical session 1, which is on sustainable generation. I'm now going to hand over to the chair of that session, Dr. Valerie Dupont, and sign off. So thank you.
So thanks, Andy, for introducing our first technical session. I'm your chairperson for this technical session. My name is Valerie Dupont, and we have a series of presentations. We start with a keynote presentation, and our keynote speaker is Dr. Vishwanath Dalvi, Vish for short. He's also from the Institute of Chemical Technology, Mumbai, like Professor Joshi is, works closely with him. He received his bachelor's degree in chemical engineering from the University of Mumbai, got a master's in process engineering from the University of Twente in the Netherlands, and then a PhD in chemical engineering from the University of Texas at Austin. He has 10 years of experience in teaching, research, and industrial consulting. His main interest is to work on technologies for rural development and rural resource monetization. To this end, he is working on solar thermal technologies, biogas generation, and process simulations. He also does fundamental work in chemical engineering, including molecular simulations and developing novel equations of states. His industrial work comprises of mathematical modeling for techno-economic evaluations of technical solutions. He has won awards for his teaching, and his academic output has appeared in top international peer-reviewed journals. So I will now pass on the screen to Vish's presentation.
Hi, good afternoon. I'm Vishwanath Dalvi from the Institute of Chemical Technology. And the talk is a mouthful. It is head-to-head comparison of natural gas, solar CSP, and solar PV with energy storage to supply a 500 kilowatt demand in a microgrid. And we have the talk is going to answer this question: which is most cost effective? Is it the PV? Is it the CSP? Or is it the natural gas turbine? Natural gas, of course, can be supplied from the gas fields, but it could also be supplied by anaerobic digestion, biogas. So the reference for data and calculations. So this is, of course, based on a peer-reviewed paper, which also has a mouthful. Title is also a mouthful. So this is just accepted in the Energy Journal. So you can take down the lead author and the journal, and you can find it very soon. So I'm not going to go through the entire rigmarole. There are a lot of calculations involved. So I'll just briefly introduce the topic, skip over most of the methodology, and then go straight to the results. You can verify everything over here. Of course, let me introduce my co-workers, Dr. D.B. Biswas, Mr. Soumyaraj Bose, myself, Professor S.P. Deshmukh, Mr. N.V. Shenoy of Srihari Industries, Professor S.V. Panse of the Marathi Vigyan Parishad, and of course, Professor J.B. Joshi, you all know from the plenary lecture. He is from the Department of Chemical Engineering at the Institute of Chemical Technology. So moving on, why are we doing this? This is why. Because of the tremendous potential of solar energy. Even if you take something as low as 600 watts per meter square of direct normal insolation and a solar to electric efficiency of only 10%, we still get 60 watt per meter square of electricity, 60 watt per meter square aperture of electricity. To supply India's 288 gigawatts of installed capacity, that would require 0.038 million square kilometers of land, including a land use factor of 0.5 and a capacity factor of 0.25, which means this is on a 24-hour basis. So this requires only 1.2% of India's land area. And just for comparison, that is this little gold square in the middle of India. So it's very possible for solar energy to supply all of India's electricity needs. Now, why 500 kilowatt? Why 500 kilowatts? So let's take the average. Let's take the proverbial envelope, and the average daily power consumption of a European Union citizen is 16.6 kilowatt hours per day. Which is now why European Union citizen? Because the citizens of the European Union enjoy a very reasonable, very good standard of living without consuming all that many resources, unlike say a citizen of the United States, and therefore this is something that we can aspire to. So the average is 0.7, hence the peak is about 25% greater than the average, which is 0.875 kilowatts. Now in India, 62 million people live in a village with an average population of 520 by the 2001 census. So 520, which is this, into 8.875 is 455 kilowatts, which is rounded up to 500 kilowatts peak demand. So this is the microgrid. It's going to supply 500 kilowatts peak demand, but it's going to supply everything in between. And this is once, so in the beginning, we in the villages have no electricity or very intermittent electricity, then any sort of electricity would be welcome. But once they get settled and get used to electricity, the demand is mostly going to look like this blue curve. There's going to be a small hump at around in the morning and a much larger demand around 8 or 9 o'clock. So this is going to be a few hours after sunset. The productive hours of PV are between 6 to 6, and the productive hours of CSP are between 9 to 3. So we immediately see a problem. The PV only, you can put in more and more PV, but all that will do is deepen the belly of this duct. So if you put 200 kilowatts of PV for a 500 kilowatt capacity, you'll get a certain belly of the duct. You put more, you get a deeper belly, and you put 464, you get a deep belly. And what happens is, if you put 464 kilowatts of PV, there is going to be a time of day around 12 o'clock when the power supplied by the rest of the units is not drawn upon at all, and that is essentially unfair to those units. So what we need is dispatchable power. So dispatchable power which follows demand instead of dictating demand. So solar PV is the cheapest renewable, but batteries for storage are expensive. Currently managed it's currently managed not by batteries, but by smart grids, which are supplied by gas-powered peaker plants. But these are inefficient compared to the efficiency that could have been achieved by a gas power plant. So solar CSP is more expensive than PV, but thermal storage is cheaper. However, conventional turbines are not fast reacting. So we need something, a fast reacting heat engine, which is steam engines. So this is the Stanley steamer car, which won the land speed record in 1906, which means steam engines are possible for power demands less than 750 kilowatts. Steam engines are more efficient than steam turbines. So here is a uniflow steam engine. And how does it work? It takes in steam, adiabatically expands. At the very bottom, it lets out the steam and then compresses. Adiabatic compresses, and then the cycle starts again. So here, over here, and over here, and over here, you get work out, and here you're doing work on it. But the work out is, of course, more than the work that is done on it, and therefore we have a net output of work. So this engine can, This is a standard 2-tank direct heating. The tanks, the hot oil can be heated either through the solar field or through the gas turbine if necessary. If it's and then there's the heat engine, which runs on the stored heat from the oil by passing through this circuit. The steam engine capture efficiency is 23. Efficiency 23%. Solar capture efficiency is 47%. The solar to electric efficiency is about 11%, which makes it about 91.2 watts of electricity per meter square of operation. The Brayton cycle for natural gas is what is used for the natural gas turbine. And that is, suppose you have air which compresses the gas to 15 bar and then expands it back to 1 bar. You get a 29% efficiency, but you notice that there is the hot gases leave with a lot of the heat. So if we can capture that heat and if you bottom it with a steam engine, we get a 35% efficiency, which is 6.6 kilowatt hours per kg methane versus 5.5 kilowatt hours per kg methane. So solar PV, of course, is given in terms of per peak watt. So solar PV is $2.2 per watt. Average value, the lower value is $0.9 per watt, which is the lowest installed in the world in 2017. Gas power is about $3 per watt. Steam power is $1.3 per watt, which takes into account everything: steam engine, boiler, air-cooled condenser, etc. Steam power efficiency lower is about $1.5 per watt, a bit more expensive. Cost of natural gas is $0.5 per kg of methane, which is natural gas delivered price. Cost of battery is $350 per kilowatt hours. The lower cost is $200 per kilowatt hours, but we'll not expect that till 2030. If we use wax for thermal storage or something of that order, then we need $128 per kilowatt hour. If we use unrefined reduced crude oil, as they call it, then this is $60 per kilowatt hour. The cost of trough is $170 per meter square, which is a standard value for troughs now. But the lower cost of trough is $75 per meter square, which we are aspiring to get. And the cost of land is $2 per meter square. So our basis is 500 kilowatt hour peak power supply is needed, enough solar harvest resources to capture daily energy to last a full demand cycle. The LCOE is calculated as the fixed rate into the rate of interest, rate of return, plus the variable cost upon the total electricity into number of days. The total electricity is 10.5 megawatt hours, number of days is 360 days per year, and ROI is 11%. So this is to supply this demand curve. On the basis of that, so we have skipped a lot of steps. So if you want, you can read the book or read the paper, but the results are quite interesting. This is the contribution of the gas engine itself to the LCOE, and this is the contribution of the bought natural gas. So you see, this is about 1/3, 2/3 price. So mostly it is consumables. So you get a base case of $0.134 per kilowatt hour of the levelized cost of electricity. Scenario 2 is if we bottom the natural gas with a steam engine. So this yellow thing is the steam engine. The steam engine would cost this much. The gas engine would cost a bit less, and then the natural gas would cost a bit less. So you get 115. If we introduce the PV in between as well, if we introduced PV plus backed up by natural gas, which is what smart grids are. So this is smart grid. We would get it slightly more expensive actually, because we have all of this. So it's actually just slightly more expensive, though you consume less natural gas. So that's the advantage. You consume less natural gas, generate less carbon, but it's slightly more expensive. Scenario 4 is just pure PV with battery storage. That is considerably expensive. That is the most expensive thing we have so far. If you have scenario 5, where we have the CSP with current costs, steam engine, and thermal storage, then it will cost 0.144, which is considerably less than the cost of the PV with battery storage, which is a very surprising result. If we added PV to the CSP mix, so PV you supply with PV when the sun is shining, and when the sun is shining, you gather in the CSP and then supply with thermal storage through the steam engine, then it becomes slightly cheaper. If you use PV with the lower cost of battery, which is not going to happen, then it's 0.129. But if you use the lowest value of PV available currently and the battery, then this is the most cost effective, even with the battery storage. However, if we go for the lower cost of CSP, then we can beat that. We can beat this. And just for reference, what would a classic diesel cycle cost? It would cost that much. So the classic diesel, right now, everybody burns diesel because it's easy to transport to remote areas and so on. But if you are going to burn diesel, you are paying a substantial price. See how this column dwarfs everything else? That's because the cost of diesel is so high. Now, this thing, is it even possible? Is it possible? Well, we are working on it. So this is already something like 75. This is already reached $75 per meter square, and as a potential, potentially it can go a bit lower. So we are working on it. So thank you very much. Let me introduce our PhD student, Mr. Puneet Gharat, and our former PhD student, Mr. Dipankar Biswas, who developed this system. So with that, I take your leave and I'll take some questions. Thank you very much, and God bless you.
Thank you so much, Vish, for this excellent and very informative presentation. However, can I ask those with questions to reserve them towards the end of this technical session and put them in the chat so we can address them all together at the very end. I'm going to now introduce our next presentation, which is given by Dr. Rolf Crook. Rolf was very recently Associate Professor in the School of Chemical and Process Engineering at the University of Leeds. His areas of expertise are in the design, synthesis, and testing of novel materials for photovoltaics and for high-resolution monitoring of solar irradiance, as well as modeling of solar resource at the local and global scale. James, you can start the presentation.
Hi, I'm Dr. Rolf Crook, and I worked at the University of Leeds when this work was carried out. This work was part of the CRESUM HYRES and EPSRC collaborations as listed at the bottom of the slide, so there are lots of co-authors who I would like to acknowledge and thank. In particular, the first three co-authors, Toby, Opio and Tanya, who are the PhD students I have worked with, and they put a lot of work into setting up the irradiance monitoring stations in Kampala, Uganda and Congo Brazzaville. There are two parts to this short presentation. The first is irradiance monitoring stations. As part of the CRESUM HYRES project, the electrical engineers require irradiance data sets as an input to their electrical models. So irradiance is watts per meter squared. It's how we quantify sunlight at a particular moment. However, there aren't many existing high-resolution long-term irradiance data sets available for Africa. Looking at the left figure, there are only 4 baseline solar radiation network BSRN stations located on the African continent. These are marked by a circle, and there are none in East or Central Africa where this project is focused. So we decided that it would be worthwhile recording irradiance ourselves. We have two types of irradiance sensors, as you can see in the photograph on the right. On the left, we have a true pyranometer, which gives a very accurate reading of the complete spectral bandwidth, but is relatively slow. We can compare this reading to global data sets of irradiance, such as PVGIS, to quantify the accuracy of the global database. On the right, we have silicon sensors, which give a very fast measurement of irradiance, but with relatively low accuracy and a narrow spectral bandwidth. The electrical engineers can use this data to make sure their electrical systems can respond to fast changes in irradiance and aren't damaged by repeated irradiance fluctuations. The pyranometer can also be used to calibrate the silicon sensors. We have two irradiance monitoring stations, one in Kampala and one in Congo-Brazzaville. It's about 800 UK pounds for each station, so relatively low cost, and because they were modular and designed by ourselves, they should be easy to maintain. The block diagram on the left illustrates the electronics we use. The station is powered by PV, perhaps appropriately, so there is no need for an external power supply. Data logging is constant, so we have a battery which charges up in the day and discharges overnight. The PV, charge controller and battery all operate at 12 volts, while the data logger operates at 5 volts, so we have a voltage regulator. The one module we designed ourselves is the amplifier board, which is necessary because we need to scale the voltage output of the sensors to an appropriate range for the voltage input of the data logger. The data logger itself is purchased as a module. It's set to record at 10 Hz, which is much faster than most data loggers, in order to capture fast fluctuations in irradiance. It records to a micro SD memory card. Once a month, the user removes the card or plugs in a USB cable to transfer the data to Google Drive. In Uganda, we have 3 silicon sensors set up in a triangle, which allows us to calculate cloud speed and direction in addition to irradiance. Also connected is a pyranometer and a thermistor in the Stevenson screen to measure air temperature. The system for Congo-Brazzaville is shown in the photograph before it was shipped. The 3 sensors have long cables, so they can be mounted several meters from the data logger. Here we have one silicon sensor on the right, a thermistor at the top, and a pyranometer still in its packaging on the left. We now have about 2 years' worth of data collected from Kampala. This slide shows irradiance data from Kampala collected from the silicon sensors. The top plot shows 20 days of irradiance data beginning on the 19th of December 2018. The x-axis is time, the y-axis is irradiance. There are 17 million samples in this data set. You can clearly see the 20 day-night cycles. The irradiance typically peaks at 1,000 watts per meter squared. You can also see that the irradiance fluctuates a lot. This is caused by clouds obscuring the sun under partly cloudy conditions, probably cumulus clouds originating from nearby Lake Victoria. If you look closely at the top plot, you can see a couple of vertical blue dashed lines to identify a single day. In the second plot, we zoom in on this day. You can now see the extent and the frequency of the fluctuations. Again, there are a couple of blue lines which now identify a single hour, and in the third plot we zoom in on this hour. You can now see details within individual fluctuations. They vary in duration and magnitude. At noon, the irradiance is falling from 1,000 watts per meter squared to about 250 watts per meter squared as we switch from global to diffuse irradiance. So we are losing 75% of the power output within a few seconds, and that is something the mini-grid will need to manage. In the last plot, we zoom in on a single minute. There are 3 plots because we have 3 silicon sensors in Kampala, and because they are mounted in slightly different positions, they detect cloud edges at slightly different times. So, moving on, the second part of this presentation reports a computer model to simulate a variety of biomass upgrading processes driven by solar energy. The model is programmed in MATLAB but it should be largely compatible with Octave, which is a free program that anyone can download. The model includes the optical, thermal and chemical parts, so I refer to it as an integrated model. We anticipate the model can be used to link together solar and biomass resource assessments to identify constraints, for example, and also as an initial design tool prior to costing, to calculate the size and number of mirrors required to process a desired quantity of biomass, for example. We've chosen to focus on relatively low temperature processes, starting with steam generation and hydrothermal carbonization, HTC. By targeting low temperatures, we only require low concentration ratios, so the demands on optical alignment can be relaxed, making manufacture and maintenance easier. Most of the work completed so far is on the optical and thermal parts, because this is where my expertise lies. The block diagram on this slide shows the three parts to the model, the mathematical methods used, and categorizes the key user inputs. The optical part of the model uses Monte Carlo ray tracing. This is illustrated on the left of the slide for two different mirror configurations. The lines represent rays of light, and each one has power associated with it, which may be delivered to the absorber. On the top left, we have a linear Fresnel mirror configuration. The tilt of the mirrors changes during the day in order to track the sun and focus the light on the linear absorber. This means the irradiance reaching the absorber is much higher than the incident irradiance, permitting high temperatures. On the bottom left, we have the compound parabolic mirror configuration. This is quite unique in providing solar concentration with stationary mirrors. It relies upon multiple reflections. Stationary mirrors means there are no moving parts, improving reliability. The color map in the middle of this slide shows the optical power incident on the absorber. In this case, the absorber is a flat plate, but it can also be a pipe. We can identify parts of the absorber that receive little incident power and would benefit from insulation or a change of emissivity. The color map on the right shows the surface temperature of the absorber and its reaching temperatures appropriate for HTC in this case. 200 rays are used to make the ray tracing diagrams, and 1 million rays are used for the regular calculations. This slide shows the output for the model, so you can see how it will be used. This example is for HTC batch processing of water hyacinth. Reaction rates are taken from literature with a reference provided at the bottom of the slide. The x-axis is time in all these plots. The top plot shows irradiance over a 10-hour period centered on noon on the spring equinox at a latitude and altitude consistent with Kampala. Under clear sky conditions, the irradiance peaks at noon close to 1,000 watts per meter squared. The second plot shows the temperature of the reactor, which heats up as the irradiance increases. The higher the reactor temperature, the higher the thermal losses, especially radiation. So the temperature reaches a limit dependent on details of the system design, in this case at about 520 Kelvin. The bottom plot shows the fractional completion of the reaction. You can see that by there is a critical temperature as expected from the Arrhenius rate equation at about 4,800 Kelvin in this case, above which the reaction proceeds. I must stress that the chemical model is incomplete and needs further work. This is just for illustration. There's lots of flexibility in user inputs to trial different mirror and absorber designs in order to optimize reactor temperature and yield. Once we have completed the sizing, approximate financial calculations can be made to establish the viability of such systems. Here are a few comments to summarize the outputs, but I won't read them out. So I finish by thanking our funding organizations, the co-authors, and I thank you very much for listening today.
So I'm thanking Rolf Crook for presenting and preparing his presentations for today's. And I'm following this with my presentation. Let me introduce myself. I'm reader in low carbon energy in the School of Chemical and Process Engineering at the University of Leeds. My areas of expertise are in combustion processes and the intensification of energy intensive processes. In particular, those that integrate the sustainable production of alternative fuels. James, the sound doesn't appear to be on. My name is Valerie Dupont. I'm presenting gasification of biowastes for GenSet fuel. And this is the contents of a Masters of Engineering project that was carried out by Harry Hanford and supervised by myself and postdoctoral research assistant Oliver Gresham. Biogasification for microgeneration for microgrids. This is used in the cases where anaerobic digestion cannot be applied to the feedstocks that are at hand. For instance, lignocellulosic biowastes are not suitable, generally speaking, for anaerobic digestion because of their low carbohydrates content. But there are many other agricultural wastes or forestry wastes that can be used as fuels via a conversion process such as gasification. In other cases, when solar PV or solar thermal or hydropower or wind power can't be used or stored, we can revert to gasification of biomass for the production of fuels. In the cases as well where there is a very large volume of biowaste, and this needs fast conversion in order to avoid worse health and safety and environmental impacts, we might want to apply a process that disposes quickly of this biowaste. In addition, there is currently in the developing world a very large scale use of diesel generator sets. So for instance, in the map that you can see in the insert on the right, there is the installed capacity in megawatts as backup generator fleets. And you can see that the darkest regions are the ones that are the most dense and present a large usage of diesel generator sets. In addition, if instead of using diesel fuel, we use producer gas, there is going to be production of less pollutant particulates and sulfur oxides and also nitrogen oxides. So by switching the fuel from diesel to a bio syngas, we are addressing a large issue which is related to indoor and outdoor pollution. And furthermore, the developing world, and in particular Africa, is ready to have a population boom. And with population booms, there is going to be large biowaste surges that come with it. We have set up an Excel-based model which combines hydrothermal carbonization of raw biomass with updraft gasification. The hydrothermal carbonization stage produces a very stable hydrochar, which can be used as a chemical energy storage medium. Following this up by updraft gasification allows us to have very long residence times in the gasification stage, thereby generating a good quality producer gas with low amounts of the heavy tars that could be damaging the GenSet downstream. We can see some of the outputs of the model in this slide. So if you look at the left-hand side table, this would show the heat and power duties of the different elements that are present in the chain of conversion, starting with the biomass mill, going on to the hydrothermal carbonization vessel, the gasifier, the filter press, separator, the screw conveyor, the stages of the gasifier, which include drying, pyrolysis, combustion, and the fans that are feeding air into the gasifier, and the GenSet. The overall GenSet production here, which is equivalent to a feed from the material balance equivalent to 100 kilos per hour of corn stover, is a generation of 88.81 kilowatts. The second table is reminding us of the main elements of kilowatt loads that are present in the chain of conversion. And on the right-hand side, you can see as an output the table of flows that are at every stage of the conversion stage. So for instance, if we look at the stream, which is using corn stover as a feed, a row, and 100 kilos per hour, we then have a flow which is milled, an aqueous media inlet for the hydrothermal carbonization. So we have a gain of water. There's a CO2 purge that is generated at the HTC stage, a hydrochar slurry that is generated as a product, and then separation into the hydrochar and processed waters. All this goes on into the different outputs, such as ash removal, the char combustion gas is generated, the pyrolysis gas, the producer gas production, the char combustion air consumption, etc. So we can use this model as a means of constructing other models that may or may not use HTC as a pretreatment of the biomass, or may not use an updraft gasifier as the main conversion of the biomass to a GenSet fuel. And we hope that this can be used as a predictive tool for the generation of power for a certain amount of available biomass, and also as an educational tool, because it actually allows the user to see what is happening at every stage of the process. Thank you for your attention, and please reserve your questions for the discussion session, which is scheduled at the end of this technical session. So this was my presentation, and it's followed by Dr. Hugh Lees. Hugh Lee is an associate professor in the School of Chemical and Process Engineering at the University of Leeds. His area of expertise is in combustion and emissions, real driving emissions. Hi, Hugh. Biofuels and alternative fuels, engine deposits analysis, engine lubricant, transport emissions, carbon footprints, and also energy audits.
Hello, everyone. Welcome to my talk today. So the topic of my talk today is widening fuel choices for sustainable electricity generation from a diesel generator. So the talk is comprised of 4 sections: introduction for diesel engine and generator configuration and principles, fuel quality requirement and the key properties from a perspective fuel specification and requirements, fuel choices, what's possible fuels for diesel generators, and remarks. First of all, this diagram is showing typical configuration of a diesel generator. You can see here, we got a diesel engines coupled with a synchronous machine or a generator to produce electricity. So you have two feedback loops. First one, you got a red line here connected to voltage regulator. That is voltage output from a generator feedback into voltage regulator, therefore adjust input to generator. And this then may change the speed of engine. If your speed engine changed, then you have a second loop, which is a speed, which means RPM. They have another loop. So RPM from engine send to speed governor. That basically send a signal to throttle to adjust the fuel flow. For example, if your RPM dropped, that send a signal to speed governor, therefore to throttle to increase the fuel flow. So that is a typical configuration of a diesel generator. This slide tries to show some basics for diesel engine operation. So if we look at a 4-stroke diesel engine, it has an intake, compression, power, and exhaust strokes. So intake stroke, so the inlet valve is open, air is sucked in. So piston is moving from a top dead center to bottom dead center. And so that is the intake stroke. Then when piston reaches the bottom dead center, at the end of intake stroke, inlet valve is closed. The piston is moving upwards to compress the air, and that is compression stroke. At the end of compression stroke, air becomes hot and pressurized. Then you're going to power stroke. So fuel will be injected at the top through the fuel injector. Combustion will happen. Then hot combustion gases will drive piston moving down from a TDC to BDC. So that is a power stroke. When piston reaches the end of power stroke, exhaust valve will open, all exhaust gases will be pushed out. So that will complete a 4-stroke cycle for a diesel engine. This is PV diagram. So PV diagram is used to describe the thermodynamic principle of the engine operation. Of course, PV diagram, you have a theoretical or real one. This is a theoretical one. So engine will start from, the cycle will start from 0. So 0 to 1, that is intake stroke. You can see the volume from V2 minimum volume to maximum volume of cylinder to V1. So that's intake stroke. After you reach the intake stroke, finish the intake stroke from 1 to 2, that is compression stroke. So pressure will be increased significantly due to compression, and the volume will be reduced from a maximum 1 to minimum 0.2. At the end of a compression stroke, fuel is injected, so combustion will be initiated. That is from a 0.2 to 0.3. So that is QH. That means heat energy is added. That's from fuel. After combustion is complete, you got a 3 to 4. That means you get pressure start to drop because combustion is completed. Pressure start to drop 3 to 4, and the volume, that means piston continue to move down. Volume continue to increase. That's a V3 to V4.4 here. At the end of this power stroke, then you got another heat transfer, is QL here. So that is one not inlet valve. Exhaust valve opens, heat will be transferred to the environment, or this is the exhaust stroke. However, remember here, piston hasn't moved yet. Piston stayed at the maximum volume, that is a BDC. Then from here, from 1 to 0, that is where piston starts to move from BDC to TDC. So that is completion of whole diesel cycle. The feature of diesel engine is only air is drawn into cylinder and compressed. That's different from a spark ignition engine. Spark ignition engine will compress fuel air mixture. And so for diesel engine, fuel is injected near the TDC. Combustion is constant pressure combustion, whereas SR engine is called constant volume combustion. For diesel engines, there is no spark plug, so combustion is based on auto ignition. So compression ratio for diesel engine is higher than spark ignition engine. That's the reason why diesel engines have a higher thermal efficiency and better fuel economy. Why diesel generators are suitable for for this off-grid application? So advantage of diesel generators: relatively low capital cost to purchase and installation, widely available. You got more choices for different engines. Portable, easy to install and maintain, robust and tough, can provide quick, cheap solution to provide electricity in rural areas. Also, one of the most important features of diesel engines is fuel flexibility. You can use different liquid fuels, vegetable oils, for example, alcohols. You can also slightly modify the engine, become a dual fuel system. Having said that, diesel engines do have disadvantages, which mainly is pollution, and also could be noisy. Availability of diesel could be a problem as well. Here is in the UK for off-road or diesel generators, all diesel fuels have to meet standard BS 2869. Here's I just list a few key properties for diesel fuel from this fuel standard. One is the serial number, minimum 45. Why they ask for minimum serial number? Because serial number is an indication how easy the combustion to start. Density here we only have a minimum, but it's not very critical. If you have a fuel slightly lighter or heavier, that's not a problem. Kinematic viscosity 2 to 5. That's just optimal viscosity. If a fuel you have a higher viscosity, you still can run engine. Flash point, that's mainly for fuel handling, safe handling issue. Distillation, that is reflection for how easy the fuel can vaporize when injected into the cylinder. Lower heating value, that is related to energy density and power output. Oxidation stability, mainly due to storage issue. If you need to store fuel for prolonged period, you need to have a good oxidation stability. Sulfur related to emissions and air quality. Carbon is related to fuel quality in terms of combustion, fuel flowing and pumping, and deposit. Also, fuel injection and spray are key parameters for diesel engine operation. So spray cone angle, spray penetration length, SMD or a droplet size of fuel spray, and surface tension, those are 4 key parameters to indicate how good the fuel injection spray. So we need a wide spray angle, shorter penetration length, smaller SMD or droplet size, low surface tension. This is an interesting comparison for the region of South Africa for diesel prices. Well, not direct diesel prices, it's mainly comparison diesel versus PV. Those yellow areas are having relatively higher diesel price, so not favored by diesel. So initially this one show comparison diesel versus PV, but that's give us an indication where you find application or potential market for alternative fuels to diesel. This just showing some examples of diesel prices in the region of South Africa. The highest one here is in Congo, Republic of Congo. Here diesel price in 2016 recorded $1.32 per liter. So some other countries also have a relatively high diesel prices. So we have to think about alternative fuels because for fuel price and availability. So alternative fuels, that could be liquid fuels, gaseous fuels, and a dual fuel system. Liquid fuels could be drop-in fuels, that mainly is synthetic fuels. That's not suitable for African countries because these synthetic fuels are expensive and not available to Africa. Non-drop-in fuels, however, that is more suitable for diesel generators for African countries or developing countries. Alcohol-based street vegetable oil, biodiesel, that's most probably feasible fuel options. Gaseous fuel could be natural gas, LPG, syngas. So interesting here, I want to see syngas and biomethane that can be produced from biomass. Then you can use that in a dual fuel engine, in a liquid gas engine system. When we talk about fuel choices, some examples here, you could use a bioethanol, but you only can blend up to 20% because of miscibility problem. Street vegetable oil, if that is produced from non-edible crops on marginal land like Jatrufa, will be attractive. You could use street vegetable oil from waste cooking oil, waste vegetable oil. It's good in terms of carbon footprint, but will have a limited feedstock. Animal fats can be used in engines, but you need some treatment like preheating or some modification to the fuel system. Engine combustion itself, you don't need a modification. You could use biogas or syngas from biomass or waste to use in the dual fuel engine system. So when we talk about the fuel choices and the considerations, there is this trilemma diagram be useful when you decide and when you say how you're going to choose a fuel. Supply security, affordability, environmental impact, and that can further split into this 9 sub parameters here. Remarks here. So diesel generators play an important role in the past and will continue to play an important role for off-grid, microgrid system even in the future. However, there is a need to expand the fuel choices to fully utilize the potential of diesel generators because of diesel availability, affordability. Biofuels, remember, including liquid and gaseous fuel. Liquid fuel, you can possibly use that directly as a replacement for diesel fuel. For gaseous fuel, if you use that in a diesel engine, you can develop a dual fuel system using diesel as a pilot injection, gaseous fuel as a supplementary fuel. The utilization of syngas and biogas from biomasses and waste in dual fuel engine can open up opportunities for widening fuel choices, helping to alleviate energy trilemma in developing countries. Finally, I would like to thank Nina, Zahida, and James for the contribution to the content of this presentation, and thank you for your attention.
Many thanks, Hugh, for this very comprehensive presentation on diesel operation principles, fuels characteristics, and what we can use instead of diesel into our diesel engines to make them more sustainable. We're now going to have James's presentation. So Dr. James Hammerton is a postdoctoral researcher for the cross-faculties GCRF and UKRI funded projects CRESUM HYRES and BEFWAM at the University of Leeds. He has a PhD from the Center of Doctoral Training in Bioenergy at the University of Leeds on the potential for blending charcoal microparticles with diesel and use it for powering diesel generators in rural areas of developing countries.
Hello everybody, my name is James Hammerton, and today I'll be presenting some of the work we've been doing on the project around predicting biomass resource availability for mini-grids. Before I start, I'd like to thank my colleague Zahida Aslam for doing a lot of the work in this area for the project. So in this talk, I'm going to firstly start off by discussing why we want biomass-based generation on mini-grids and why this is really important. Then I'm going to move on to some of the examples that are already out there where it's been used, and some of the challenges that have been raised through the operation. Next, I'll be talking about what are the kind of operational considerations when using biomass. It's very different issues than you would have with solar PV. And then finally, I'm going to discuss how we can model this challenge and how we maybe can solve some of these problems. One of the real advantages of using biomass for mini-grid generation is that we're able to produce electricity regardless of the weather or what the time of day is. And this means that we're less reliant on batteries to cover up some of those dips in supply. Usually this is done using fossil fuels and engine generators, and these are great from an initial cost perspective. We can get engine generators quite cheaply, but it's really the diesel that is expensive, or what other fossil fuel you might be using. Where these mini grids are, they're often rural, and that means there's a lot of biomass available, whether this be from agriculture, from animal waste, from forests, and this is potentially a really cheap source. The real downside though is that the biomass is cheaper than the fossil fuels, but there's some issues that can arise from actually using it. So just a quick overview of the 4 types of biofuel we're really looking at in this project. We start off with gasification and biogas, which are I suppose the leading electrical generation from biomass on grids. And what's great about these is they're using waste biomass often, and this is often from agricultural residues or other farming practices, and they're not quite in competition with each other. They often use different types. So gasification uses quite dry things, quite woody things, whereas biogas is using things like dung or food waste. One of the real downsides to gasification is that we've got quite long startup time. So usually the systems are planned to operate for a certain amount of time a day. On the other side, biogas potentially is being produced all day, and we can potentially use it as and when we need it. So looking at 2 other options that we've been considering that are much less seen but have certain advantages are vegetable oils and ethanol. These are usually more expensive than gasification and biogas fuels because we're not using wastes usually, but they can be stored quite well, and they're potentially more suited towards backup generation, and we can store these for quite a long time. So just going over some of the systems that are already out there, we usually see that when there is biomass systems, it's gasification. There's some biogas systems. Often biogas systems are actually connected to the main grid because they're usually at large farms. They might have hundreds of cattle, so they're producing a lot of electricity, and they usually connect to the grid. What we often find is that the systems are oversized. There are issues with supply chains and getting the biomass, even though it shows that there's a lot of availability in that area. We often have high capital costs, and often the systems are either too complicated, or you can say that the operators don't have the technical capacity to operate them well. So a company called Pamoja has set up a gasifier in Uganda, and it runs on corn cobs, so it's using some of the waste produced by the community. But the real issue they've sort of faced is that it's oversized for the demand that they are trying to meet. And this is in large because there was going to be an industrial area connected to the grid to provide demand, but this hasn't come to fruition. And unfortunately, what's happened is that the load that's typically seen in a day is lower than what they can actually produce. So we need to maintain temperatures in the gasifier to actually produce the syngas. And if we drop the load too much, it gets too cold and it won't produce the electricity. So that's a problem. Another sort of problem is that it uses wet scrubbing, and I would really hesitate to use a wet scrubbing system in a rural developing country mini grid setting, because it produces this watery toxic waste that's quite difficult to get rid of. I think you're better with using like catalytic systems. I have another example for you here using anaerobic digestion, and this is in Peru, and they've got a communal farm of 67 animals, which is providing electricity for about 50 households. So it's been working quite well, and they've been producing biofertilizer, which is actually the most valuable product to the system. But we're still seeing that compared to the high initial cost, it's very hard to see how this investment will ever be recuperated. So we can argue, is it that sustainable? I'm not too sure. So I want to go on to the operational considerations for biomass systems. We have things that could happen. We might have a seasonal power demand. It might have to operate more in months where there's not as much sunlight. Are we expecting the demand to increase in the next few years? With development, people are buying more electrical goods, and we would sort of expect that the amount of electricity that we need to produce will go up. And then looking at the biomass supply, we're probably going to see that if we're using agricultural wastes, they're going to coincide with harvest times. We're going to have a lot then, and we're going to have to store that for a number of months. Also, the type of biomass we have available might vary at different times a year, and we're going to have to consider that. And if there are any issues with the supply chain, if companies drop out that were supplying you with their biomass, are there alternatives we can use to make sure we can still produce electricity? So what you'd usually find is that transportation of the biomass to where you're using it is going to be the biggest factor in the cost, because we're often using agricultural wastes that have little to no value. How we can get around this a little bit is tying the system to productive use. So if there's, say, a rice husk dehuller, then that could be, we could be producing, I guess, the waste on site, and we can put it directly into the gasifier. So that's so tying it into productive use could be a really good way of sort of getting around these problems. So how we're trying to solve this problem is we're looking at a software package that can help grid planners look at what's the best biomass to collect based on where it is in relation to their station, how much it's going to cost, how much it's going to store, and potentially the preference. So certain things may mean that you have to maintain your equipment more if it's not good quality as another type of biomass. And what we can do is we can assign that a cash value to compare all the different factors together. What we're also doing with the software package is assigning a delivery cost in terms of distance and the volume which we need to collect, and it's just a single distance at the moment. What we can do with this program is we can find what the marginal cost is of the biomass, and this is really important because really when we talk about what's available, it really comes down to the money. We're limited by how much we can pay for our biomass because we need to produce electricity to a certain sort of price. So if we find the marginal cost, we can find out what would happen if we have to produce more electricity, or we might think, well, perhaps it makes sense to produce less electricity through biomass and maybe move on to using solar photovoltaic panels instead. So at the moment, it's a simplified transportation model that we're going to improve on in the future, take into account the different terrain. So this is using simulated data, and it shows you what the software package it will do. It can tell you, as you see on the left, it can tell you what level of storage you need at your site to make sure that you always have enough biomass. It's going to tell you when you need to collect your biomass. And then on the right, this is the marginal cost. So you can see that we're going to likely want to collect the biomass that's closest to our site first, and eventually it will get more expensive. So perhaps this will affect where people want to place the power station in relation to what kind of biomass is available. So we're going to move on, and we are at the moment moving on to a more complicated version that's going to take in a few more factors, but we're going to make sure it's going to be based on freely available information, and hopefully it won't need the user to have too much technical skills to operate this. So this system is going to take into account the infrastructure network, the roads in the area. And what we're going to do is we're going to use OpenStreetMap, which is freely available maps, and we're going to put that into MATLAB or Octave, which is a free version of MATLAB. And we're going to map those roads in relation to where the biomass is. So what the user can do in this situation is they can add the location where the biomass is being produced, and this could be through surveys of households or businesses that are producing biomass. Or we might want to use remote sensing if it's harder to get to the location and do all that manual data collecting. So in our MATLAB model, it's going to map the roads, and it's going to take into account the different types of roads that are available. And then in this, the software will place on that where we're producing the biomass and where we're thinking about where we're going to put our biomass station. And then we're going to crunch the numbers. We're going to find the distance between all these points. And then we're going to use a traveling salesman algorithm, because in many of these places where microgrids will be, there's going to be a lot of small farmers producing small amounts of biomass, and we'll probably have to collect, if we're using, say, a large lorry, we might have to make quite a few stops. So we want to find out what's the shortest route. So from that, we can then start to take out the source of biomass that are too expensive, and we're going to sort of get down and find the cheapest network that we can make to keep that cost of biomass and therefore the cost of electricity down. So in conclusion, bioenergy systems usually look really good on paper because of the low unit cost per kilowatt they can produce, but they frequently run into problems along with the operation. Often this is where we can actually find the biomass, even though we know that there is a lot there in the area. And open source software could be a really good tool to use to sort of get around some of these issues. And again, household surveys and remote sensing data can be really useful information for us to actually work out where the best place is to put our biomass using power station. So yeah, thank you for listening. I look forward to hearing any questions.
So thanks so much, James, for your presentation. We are really looking forward to your model that will allow to make people use their gasifiers, which are oversized currently at the right power, if they have a tool like the one that you're working on. So our next speaker is Nina Rangel Ortiz. Nina is a postgraduate researcher in the School of Chemical and Process Engineering at the University of Leeds. Her research focuses on the optimization of diesel generators for better integration of biofuels and solar power in hybrid microgrids for rural electrification.
Hello, my name is Nina Rangel Ortiz. I will present a cost optimization model to assess the effect of biofuel utilization and solar power integration for a better planning of PV diesel microgrids. Today, I will mention a general background to understand the situation of diesel microgrids around the world. Then, I will mention the objective of this presentation, and after that, I will explain a little bit about the performance of diesel generators to introduce the cost optimization model. Finally, I will give the conclusions of this work. As a background, it is important to know that diesel-based microgrids are widely used around the world because they have low capital cost. Generally, mini-grids are small diesel and hydropower systems in developing countries. Rural electrification relies on diesel generators, but it is unsustainable due to price volatility, fossil fuel availability, and their environmental impact. Diesel microgrids have high operating costs related to their fuel consumption, and it could be higher if the generators have a poor performance. The objective of this presentation is to explain the importance of developing a PV diesel microgrid planning tool to minimize the operating cost and the environmental impact of diesel generators by incorporating the use of biofuel within solar diesel hybrid systems. To understand the importance of this model, it is necessary to know where is this operating cost coming from and how it could be possible to minimize. By looking at the bottom branches of this diagram, it is clear that the operating costs and the pollutant emissions are related to the fuel consumption. So the question is, how can we reduce the fuel consumption? And the answer is related to the diesel generator performance. The performance depends on the output power of the engine, and it is affected by the engine design and the engine size, but it is also affected by the quality of the fuel, especially if we want to use biofuel, as it has different properties compared to those from diesel. Two other factors can also affect the engine performance. These factors are the share of renewable energy included in the system and the low demand to be supplied by the engine. Let's look at one of the factors affecting the fuel consumption. The figure shows the fuel consumption of a 5.7 kilowatt diesel generator that I used during my lab work at different output powers. As you can see, the higher the output power of the engine, the higher the fuel consumption. The same trend is shown by this figure, but the difference is that here several engines of different size operating at different conditions are included. It is clear that higher output power refers to higher fuel consumption, but with the equation shown, it is possible to estimate the fuel consumption if the required output power is known. Now, let's see how we can achieve a good performance of a diesel generator. This figure includes the fuel consumption, represented by the blue line, as explained in the previous slide, but it also shows a green line, which represents the break-specific fuel consumption, or the relationship between the amount of fuel consumed per unit of electricity generated. The best specific fuel consumption values will always be found if the engine operates above the 55% load. And again, these are the findings from the engine that I was using during my lab work. If we want to know about the performance of other engines running with a biofuel blend, for example, castor oil and diesel, we can look at these two other figures. Both of them show that the best break-specific fuel consumption values occur when the engines operate above a 55% to a 60% load. That is why we should always operate the engines within the acceptable region, which is above 60% engine load. If we know that engines should operate above certain load, it is necessary to know how much power the system will require from them to select the right size. The selection depends on the load profile and the available power from renewable energy. For example, if the system has a certain PV installed capacity, we should select a group of engines able to supply the right demand while keeping the right operating conditions, instead of selecting one big engine able to supply the peak demand, but showing a poor performance during the rest operating periods as a result of its low load operation. Aware of the factors explained before, I implemented a Python-based algorithm to solve a cost optimization problem, able to select the right size and the right number of generators, considering the size of PV installed capacity. The model also selects the convenient biofuel blend, considering the fuel costs and the emission costs. This is how the objective function of my optimization problem looks like at the moment, but it will be modified to include some other costs as part of my future work. Probably you are still doubting about the importance of having a model like this, but it is estimated that more than 7,000 mini-grids will be implemented for global development, and they will be mostly solar or solar hybrid. About 4,000 are planned for Africa, and this is why I am interested in showing the example of Tanzania, as it has around 109 mini-grids, but only 3 of them are hybrid systems. From the pie chart, we can appreciate that there is a need to implement more hybrid systems. As I mentioned before, Tanzania is a location of interest, and this map shows the existing mini-grids in that country. I selected the Pigamiti rural area as a possible location for a hybrid system. And also, I used the values from this table as inputs to run the cost optimization model. You can see that there is a diesel price, a castor oil price, carbon tax, and the different purchase price of the gensets depending on their size. These are the best case and the worst case scenario results from the optimization using a high load profile with the respective PV installed capacity. The lowest cost corresponds to the Triple H scenario, and the highest cost corresponds to the HLL scenario as shown in the table. Besides the difference in the total cost calculated for the first year of operation, it is relevant to look at the genset selection as it shows the different combinations for each scenario. A bigger engine is required when less PV installed capacity is available. But for all the cases, the engine will work within the recommended region and the cost will be minimized. Similar results were generated for the medium load scenario, but with a different combination of gensets, including Genset 1 and Genset 3 instead of using Genset 2 or Genset 4 from the previous case. For the low load scenario, only Genset 1 and Genset 2 were selected. This prevents unexpected break-specific fuel consumption and reduces the environmental impact of the system. So, from the material presented, the conclusion is that the performance of diesel generators is affected by the load and the share of PV included in the system. A poor performance increases the operating cost, but a better selection improves their performance, avoiding excessive fuel consumption and reducing environmental impacts. This cost optimization model allows a better integration of PV and biofuel during the planning stage of microgrids to design more sustainable systems. Thank you very much for your attention.
Thank you, Nina. This was really, really interesting and very important as hybrid systems are likely to increase all over the developing world. And it's good to see that you are looking at specific case studies to show the validation of how choosing the right combinations and sizes of engines is vastly important in terms of maintaining the efficiency of the overall generation system. So we are really looking forward for further work into this. Now, this was the last presentation in our first technical session, and we're now going to open up a short session on questions and answers and discussion. We're exactly at the right time to start this. And so I would like people to either write into the chat for questions to the presenters. Some have already been occurring, that's great. Or raise their hands if they want to actually put their questions and as a viva voce. We have 15 minutes until 11:20 when we're going to have a break of 20 minutes, after which the second technical session will start. So we have a first question from Jon Lovett. James, can you tell us a bit more about the economics of your byproducts?
Yeah, sure. So I guess this is in sort of I suppose discussing productive use. Now I think that a lot of the sort of a lot of the case studies show that how important productive use is, because you know, communities are often quite poor. They need to find a way of paying for the electricity, and obviously through productive use, there's a use for electricity that's generating income. So definitely, I think in terms of, say, if you had a rice dehuller, you're making more you know, you're making more money through that. But I guess certainly the rice husk is, you know, obviously, you know, a huge waste. But if we've got productive use, we all of a sudden have quite a large amount of this waste in one place. So it's going to really bring down the costs of actually producing the dehulled rice, because we're potentially getting electricity for a very low price because we're using those wastes. So yeah, I think it's certainly, you are just sort of, I guess, making money wherever you can, really, and I think that's really important in developing countries, that everything that can be used is used. Yeah, essentially, is what I'd say on that.
We have a question from Andy to Vish. Vish, can you tell us a bit more about the integration of the solar thermal with the steam engine and generator? What scale do you think this could be done at? And what would be the limiting factor for scale, size of the CSP or size of the engine?
Hi. Just a minute. Let me take. Hi. Hello, Andy. What? Yeah, I just sorted out the echo. So the maximum that you can take a steam engine, I think, is about 80 HP, 80 to 100 HP, which is about 80-90 kilowatts. So if you want 500 kilowatts or so, you will have to use several steam engines, several cylinders. That said, a steam engine's efficiency is substantially decoupled from its frequency. So you can drive the steam engine slower and it will still produce the same efficiency. So you can use the steam engine as a load following device, which is really valuable in case of something that you want to use as a backup for a solar or intermittent generating renewable system. So let me just quickly look at what the other part of the question was. Integration. Yeah, the integration. Can I just quickly show you my screen?
Yes, you can.
Yeah, thank you. So the integration will look something like this. Yeah. So this is an integration of solar field, gas power cycle, and a steam engine. And if you can see my cursor, what happens is when everything revolves around these two tanks. the solar field collects the solar energy when the sun is out and essentially tops up the hot oil tank. And the hot oil tank draws oil at a rate depending on the demand of heat from the demand of electricity from the system, and it will generate. So that this heat exchanger will have to be designed in a sort of careful way. We might have to have several heat exchangers which work on and off. There are ways of doing that. So this heat exchanger will have to be done so that it can take variable loads. And then the steam engine, of course, can take a variable load, no problem. And so the steam engine uses the heat generated by the hot oil. The heat from the hot oil is used to raise superheated steam, which drives the steam engine, and it is condensed either to the atmosphere or to another bottoming cycle. And the cold water comes back, cold water which is 100 degrees comes back and is reheated through the heat exchanger. The hot oil goes through the heat exchanger and becomes cool oil, which is still very hot, and that is sent through the solar field again and again. So one advantage of this system is you don't really need, because you already have storage, the storage tank acts as a buffer. So controls become really simple. So you have a very large, buffering system that can insulate the vagaries of the solar field from the vagaries of the demand. So the demand side of it, or the supply side of it, is essentially, or this is the demand side. The demand side of it is substantially insulated from the vagaries of the solar field by these two tanks. So even if there is a cloud, or if there is if the sun goes down, or there is whatever it is, you still have the buffer offered by this tank to take care of the intermittencies over here. And then at worst comes to worst, when there is the monsoon, when there is no sun at all, at that time you can use the gas power cycle. So that's how you do the integration. So you don't need extraordinarily complex electronics or algorithms, because these two tanks act as buffers. Is that did I interpret your question correctly?
Andy says yes, excellent.
Oh, okay. Thank you so much.
You have further questions in the chat. If you want to address them, can you have a look? If you stop sharing your screen and go back to the meeting.
What is the gas turbine doing here? Yeah, the gas turbine is well, at some point, if you do need backup, then so the gas turbine is there to show that it is possible to integrate a gas turbine in this system as well, if you need to. If you wanted to integrate a gas turbine, you could do it. So that's what it's doing there. It's not really. So if you have a gas turbine, it's going to act as mostly a backup, especially in times when there is monsoons, when the solar system just won't work. Then in places where the solar system won't work because of seasonal lack of direct sunlight, then we have a gas turbine. Any other questions?
Andy was also asking, is that the next phase for the steam engine, the new steam engine revolution?
Yeah. So what we were thinking was along that this would be called a new age of steam. It would be sort of a new industrial revolution, and it would be, because a lot of if it takes off in rural areas, then that would be the case. Let me just address this question by which says steam engines are usually not suitable for intermittent operations. And what is the efficiency? So I'll address the first one. That's a really good question. And the answer to that question is steam turbines are not suitable for intermittent operation, because they are steam turbines, especially the vacuum turbines, those are operated at low pressures. they are massive machines. And they take about a week to get up to speed. And once they get up to speed, there's no stopping them without just shutting them down. So steam turbines are usually not good for intermittent operation. Steam engines are really good for intermittent operation because you can actually run a car with a steam engine. And people have run cars. There have been a very successful line of cars called Stanley steamers. And cars are essentially intermittent operate. They stop and go, stop and go. That's what they do. So steam engines are really good for intermittent operation. A steam turbine isn't. And what is the efficiency? The efficiency of this steam engine is about 23%, between 20 and 25%. And,
that's great. Thanks, Vish.
Yeah.
We have a question from Cheng Wen. Cheng is our postdoctoral research assistant on the socioeconomic work packages of the CRESUM HYRES project. And Cheng is asking, Nina, is the cost of battery normally an important part of the overall cost of a diesel photovoltaic hybrid system? Have you considered the cost of different battery technologies?
Yeah, thank you for the question. Yes, normally batteries are really affecting the total cost, and precisely that was one of the reasons I decided to do this model without considering the battery, and also to avoid the environmental impact, because there is no homogenized law to recycle them. So as we are looking for minimizing the cost, in this time I am not considering the battery system. Yes. Is that okay? Or
thanks, Nina. Cheng? Okay, I expect that this is fine. We have a question from Gaurav Nahar, who's our industrial partner and also part of our advisory group in India. He says, hi Vish, will the gas turbine cycle run on biogas or hydrogen rather than natural gas?
Hi Gaurav. The gas turbine cycle will run really well on biogas, provided we scrub it off the silicates. If we get out the silicon compounds, then there is no reason why it can't work on biogas. It will also work really well on hydrogen, except that if you have hydrogen, hydrogen is really expensive. If you have hydrogen, it will cost something like 6 pounds per kilogram. So if you have hydrogen, one would really like to use it to make something more valuable than just burning it. So if we get a really reliable source of hydrogen, what we would like to do is compress it and sell it and get the price for it, because hydrogen is pretty pricey. But natural gas can really work on biogas, absolutely.
It's a very good point about hydrogen.
But we can use solar thermal to generate hydrogen in the cycle, isn't it?
Yeah, with great difficulty, because the lowest solar chemical cycle is it needs a high temperature of 500 degrees centigrade. The copper chloride cycle.
So what about steam ion process?
So which one? Steam ion process. Oh, I'm not sure what temperature that will need. What is the maximum temperature that will need?
Pass it over a hot ion catalyst, which would reduce steam to hydrogen.
Yeah, but then how do you regenerate the catalyst? That will require a pretty high temperature.
Yeah, but then it will be like a looping, working on biogas, oxidizing the material.
Yeah.
So it could be a combination of that.
Absolutely. But even then, if you do have a looping system, which is itself a pretty difficult thing to do. But if we could do it, and we could make hydrogen out of it, then we just sell the hydrogen.
Or we could not run it only on hydrogen. but it would be, like using a high-tane mixture, which would help in burning biogas much efficiently than burning biogas alone.
Oh, absolutely, absolutely. Hydrogen is a wonderful thing to have. Absolutely. I'm not saying it won't work on it. I'm just saying if you have hydrogen, there are more cost, more lucrative outlets for it. That's all I'm saying. So it will work. Your question is absolutely right. Hydrogen can absolutely run a gas system. No problem.
You might argue that the hydrogen could be well used into combustion engines of heavy-duty vehicles, just the heavy-duty ones. Hugh, do you want to comment?
Yes, yeah. If we have a hydrogen, actually, Vish, you mentioned the price £6. That is optimistic. In the UK, the hydrogen price roughly is about £10. So it's not that cheap. £6 would be optimistic. Yes, if we have a hydrogen, you got an option where you're going to use it. You're going to, for example, for heating, for space heating, or for heavy-duty vehicles like trucks, we're using fuel cell, or basically, are you going to use a fuel cell as an electrified powertrain, or you use it in a combustion engine as a fuel in the conventional combustion mode?
I think for us in the UK, hydrogen for heating makes sense, but not in the global south, where heating demand is so low.
Yeah. Well, in terms of, because if you look at the efficiency, fuel cells efficiency now is about 60%. Internal combustion engine, the best one still 45%. Even best gas turbine reached about near 50%. So that's still lower than fuel cell. Of course, the problem with fuel cell is reliability and lifespan. And the power output also not high enough. That probably is a problem.
Well, thank you all. I have to now close down this question and answers session because we've reached our timetable limit. And we're having now a break of 20 minutes. So if you could all just mute yourselves and you could all come back at 11:40 when the second technical session will start. So I'm thanking again hugely all our contributors to this morning's presentation. It was, we realize it's a lot of work to prepare your presentations, narrate them, or just present them, and also to go through the whole preparation process. So thanks again. And also to our delegates who have contributed to very interesting questions. So we'll see you later at 11:40 UK time.
Hello, is everybody back? Okay, looks like everybody's back. Hope you had a nice break. But in the past, if without COVID, we could have some snacks, have some drinks. Unfortunately, you have to make drinks by yourself. And that's something we can't do anything. Anyway, I think we had a very nice session this morning. There's key speakers and all these presenters gave a very interesting and very diverse talk. And so now I hope everybody's back now. Okay, I'm just monitoring that. Okay, so if everybody's back, can we continue, please? So I'll introduce our first speaker for this second technical session, case studies in renewable energy generation. So the keynote speaker will be Dr. Mary Susan Abel from Crook, Uganda. Dr. Mary Susan Abel is the managing director of Crook, that is representing the Center for Research in Energy and Energy Conservation in Uganda. So Crook is a not-for-profit organization based in Macquarie University in Kampala, and they play important role in influencing change from traditional forms of energy to sustainable and clean forms of energy. Mary is involved in a number of projects linked to Leeds University, including this project, CRESUM HYRES. She is also one of the founders member of EPSRC, and also the Clean Energy Research Alliance. And she is the principal investigator in Uganda for 3 major international projects with Leeds, which is a Royal Society Defeat project, and this CRESUM HYRES project and the Biofuel project. So we are ready for Mary's presentation now.
Hello, everyone. I'm Mary Susan Abel, the Managing Director at the Center for Research in Energy and Energy Conservation at Makerere University in Uganda. Today, I'll present on the limits and prospects of renewable energy development in Africa. Looking at the electricity access, you can see the numbers are still low, with the East African region registering the lowest figures on both access and the per capita electricity consumption. A number of initiatives already to extend the grid, working through proposed power pool projects and partnerships with development agencies. Renewable energy has got a lot of potential for meeting the energy demand in Africa, as you can see, moving towards 2030. The proportion of renewables like solar PV, concentrated solar power, biomass energy, hydropower, wind, geothermal will play a big role. Although Africa has the lowest primary energy use per capita per year, you can see from this graph, it also has the highest land to energy use ratio, and that is a great potential that can be harnessed to increase renewable energy in the energy mix. In 2014, Crook was involved in a study with the International Renewable Energy Agency, together with energy engineers across 21 countries from the Eastern and Southern African power pools, and using a multi-criteria zone ranking tool. Resource assessment was made for selected technologies to create project opportunity areas to guide the governments in planning for renewable energy developments. The most weighted factor in the multi-criteria attributes that were used in the study, as you can see here, was the levelized cost of electricity. As a result, it's very clear again that the potential of the continent in terms of solar PV is quite high across the regions. Potential on wind is also mapped here, with the red showing the best opportunities for development. You can also see opportunities here in East Africa. The potential for developing wind, solar PV, and solar concentrated solar power. This is based on the levelized cost of electricity in dollars per megawatt hour, with the red showing the most opportune areas. And this kind of maps can be used by the governments to plan better. So in terms of the limits, as a summary, based on experience and involvement in several interventions in renewable energy in Uganda and East Africa, we can look at these 10 points. Weak institutional frameworks, inadequate infrastructure, lacking policies for better renewable energy planning, poor coordination and linkages of existing renewable energy programs, pricing distortions within the technologies, high initial capital costs with challenges in accessing finance, poorly designed dissemination strategies, and on the technical side, gaps in skilled manpower to design, install, operate, and maintain renewable energy plants. Very important, poor access to quality and reliable baseline data, information, and knowledge to inform decision processes, to inform investments, to inform development partners on which priorities to take, and gaps in operation and maintenance, both in terms of planning and implementation. But there are a lot of prospects as well. Renewable energy has prospects in increasing installation of decentralized systems in areas where the centralized grid cannot reach, or in areas where it is still too costly to invest in centralized grids. There's a lot of potential for economic development, environmental benefits, and social benefits for communities, because renewable energy plants are usually very labor intensive. Opportunities for local manufacture and energy entrepreneurship for the youth and the businesses in these countries. There are several training institutions already existent in countries like Uganda, and developing innovative curricula to build capacity of young engineers, youth on renewable energy technology installations, troubleshooting should be taken advantage of. There is opportunity for community engagement with the decentralized systems. The communities can define their user needs and participate actively in the planning, implementation, and operation of plants. Some countries have already started designing policies to target a large-scale dissemination of renewables, and the different programs can take advantage of these policies to accelerate development. It is possible for renewable energy technologies to be developed in a modular format and be scaled in stages. And this is a uniqueness and an advantage that renewables have over the conventional energy systems. A number of development partners are very interested in supporting renewable energy projects, and research groups have started to realize the relevance of partnership for greater impact. And the sector can use this to accelerate programs to get accurate data and information for decision processes to improve access to financing. Some governments have established agencies or organs that run and manage renewable energy funds, and that can be used to motivate and support private sector to develop mini grids in the rural areas to improve rural electrification and to encourage more innovation in financing. And finally, regional integration is possible. For instance, looking at the East African power pool and the Southern African power pool to better use the energy resources in the regions and thereby increase access, and not just in the countries, but in the entire region. The International Renewable Energy Agency developed a renewable energy roadmap for Africa to see it increase its proportion of modern renewable energies in the energy mix from 2013 to 2030, from 5% to 20%. And as you can see here, biomass alone would have a contribution in electricity, contribution to the transport sector, residues from agro waste being used in industry, and other fuels used in appropriate cooking technologies. The renewable energy proportion will be much higher than 22%, but this is the target for modern renewable energy proportion in the energy mix. In order to achieve and implement all the recommendations and take advantage of the opportunities that we discussed earlier, there's need for investments, and these are the estimates for all the 5 regions in Africa, totaling to $381 billion US. And this table is showing the renewable energy targets by some countries to demonstrate the understanding of the potential of renewables and commitments that are underway by different governments. Some of the targets are ambitious. Nonetheless, it's a step in the right direction. As you can see here, this column on the share of electricity, these are percentages for Uganda. You may not be seeing this very clearly, but Uganda had 61% as a target for 2017. Now under view to see how to achieve that with this period. Kenya, for instance, has a target of installing 5,000 megawatts of geothermal by 2030. In order to achieve all this, the recommendations have to be implemented. The policies have to be reviewed, specifically targeting increasing the renewable energy proportion in the energy mix. Crook and its partners, Crook working with the SERA team of researchers in renewable energy, will contribute to knowledge, data, planning tools, and generally research outputs that can inform policy, can inform planning and investments in renewable energy for Uganda, for East Africa, and other countries. At Crook, we have a regional testing and knowledge center on bioenergy to support the sector in developing bioenergy technologies, both on small scale and large scale, working, of course, with our partners from SERA. Thank you very much for your attention.
Thank you, Mary. Very interesting talk to give us the overall holistic view on the policies, on the situation, and on the progress in the whole Africa and also in Uganda. That's really good. Very nice. So our next speaker will also be from Uganda. So that is Opio. Let me just find his, yeah, Opio Miria is next speaker. He's a senior researcher at Crook, same as where the Mary come from. Okay. He's currently completing his PhD. It's a bit echo there. Yeah. Okay, let me just try to remove this echo. Yeah, okay, that's done. So he's currently completing his PhD on a project based on carbon slurry fuels at Crook, funded by this Royal Society or DFID project. He's participating in the technical aspect of CRESUM HYRES, Biofuel, and the EPSRC project, which Mary mentioned in her presentation. So Opio has a vast experience of renewable energy technologies and hands-on experiences on testing and operating a range of renewable energy generation. His talk today will focus on his experience using small-scale gasification. So now the screen will be Opio.
Good morning, everyone. My name is Opio Innocent Miria, a researcher from Research in Energy and Energy Conservation University. I'll be presenting a case of small-scale application in support of creating resilient, sustainable microgrid project. While looking at the potential of bioenergy in Uganda to support such project. You are welcome to my presentation. Energy being one of the most essential resources, it is also being governed by the government. And within Uganda, there is institutional framework that govern the extraction or generation of energy. And one of the arm of government responsible for that is the Ministry of Energy, together with other regulatory authority such as the REA, that supervises other companies that are within the generation, transmission, and distribution. So therefore, they guide the different activities that happens. So if we are to implement this microgrid also, we have to consult each of or some of the companies or the parastatals as they are stakeholders in such a project. Therefore, since we are looking at the potential of bioenergy in supporting microgrid, first of all, in Uganda, we are looking at, we have to look at what is the energy potential that supports or that can support our proposed project. Of course, there are many energy generation options in Uganda. Among them include hydropower with a potential estimate of 2,000 megawatt, biomass resources with about 1,600 megawatt, solar with about 200 megawatt. Wind is a bit insufficient here for especially large-scale electricity generation. We have also geothermal, although not fully exploited. I think most of the projects are still at exploratory stage. We also have peat, which have also been estimated that it can produce about 800 megawatt. Recently, about 5 to 10 years ago, we also discovered oil to about 6.8 billion barrels, of which, although only 1.4 billion barrels can be recovered, but all these resources contribute to supporting any energy projects such as the microgrid. So since we are looking at specifically the contribution of bioenergy, we have to first look at what is the present situation, the energy mix in Uganda. Of the potential I mentioned in the previous slide, we have only installed 1,252.4 megawatt. That is as of this year, 2020. Out of that, of course, there are many technologies, or it is coming from many technologies and resources. Like the large hydropower is the main contributor. Since we know River Nile started from Uganda, and in Uganda here it contributes to most of the potential sites for electricity generation. Although also there are other small hydropower spread across the country, which is also contributing to the total capacity. And we can also see that the total capacity is coming from thermal, that is heavy fuel oil, from cogeneration, from diesel, from solar, and from biomass. Within this context, the contribution of biomass is coming from the cogeneration, that is using the bagasse, as well as using the biomass, which is the solid biomass that we use in gasification. So to support our microgrid, what bioenergy resource potential do we have? Looking at that map and the data, it gives us an idea that we have like standing trees to a tune of 26.3 million tons per year. Of course, there are different technologies that can convert that into the different electricity sources. However, knowing the potential will help us to adequately know how much of the bioenergy resources can contribute to a microgrid. So we have the different types of biomass, like the tree that are standing, like the waste from agricultural activities, also waste from forest activities, that all contribute to that. Also, opportunities for investment within bioenergy that can support projects like the microgrid include like previous studies that have already been done to clearly give us models that exist that we can use to implement similar projects. For example, such models have indicated that if you look at the map, we have proposed sites of labeled from A, B, C, D up to H. And the model here is looking at how are you going to supply especially the feedstock, for example, for gasification, if gasification is to support our microgrid. So we have seen that such models exist, and it gives us a clue that either you can buy it from those who are already having it, growing it, or you can individually create or grow it on your private land, or otherwise, also in other options, we shall see that there are options where corporate organizations such as tea factories that are already having plantations to support their tea drying, they can still use that to generate electricity to support their activities. That is to support the microgrid within such an area. So yes, bioenergy can support microgrid, given that there are already models also that have been developed to support that kind of understanding within that. Apart from that, there have already also been studies within Uganda that clearly spell out the different types of tree species that can help us to generate enough or high yield of biomass to use it for power generation. For example, that species, we are able to harvest it within 2 years. An example of also eucalyptus grandis, which also matures especially between 4 to 8 years, we are able to harvest to support that kind of project. Therefore, what technologies or conversion technologies do we have on the ground that can enable bioenergy to support this kind, the microgrid project? We have mainly two technologies. One is the combustion technology, of which within combustion technology we have different types like the steam engines, or organic Rankine cycle, and cogeneration. So it means we use this to generate combustion. It means you're burning it to generate heat, and you convert that heat to generate steam, and then you use the steam in each of those equipment. However, on the ground, we do not have steam engines, we do not have organic Rankine cycle, but we have cogeneration, especially being done by the sugar factories. So in simple term or illustration, cogeneration is where you're using bagasse to burn it in a boiler. The boiler produces steam, steam runs the steam turbine and then produces the power. Meanwhile, the processed water is channeled back and as it is recycled. And it is evident that in Uganda, there are many cogeneration power plants. For example, Nyara, Kakira, Kaliro, Skol, Mayuge, all these are sugar producing companies, and they are found easier because they have the feedstock. And it is contributing up to 119.6 megawatts. So we have bioenergy resources in the form of bagasse that is able to support microgrid and even national grid in our country. Another conversion technology, of course, is the gasification, of which we have different types of gasification. But specifically, what we have experienced here, we have two main types due to the sizes of what we do have on the ground, especially the updraft fixed bed and downdraft fixed bed. And we have also some few sites that has been installed, like Pamoja Tiribo, which has 0.032 megawatt, and also Pamoja Sekanyoni with 0.01. And also there is one in Kalangala Island that is also having about 1 megawatt. So in total, gasification alone is contributing to about 1.04 megawatt. So what is our experience within this field? At CREEK, or at Center for Research in Energy and Energy Conservation, we have undertaken some of these projects before, especially implementing in areas where we are doing it as energy for productive use, where farmers could convert their waste into electricity and use that electricity to improve the economic value of their crops. So the technologies we have interfaced with coal. One is the second one is the Husk Power. The third one is APL, that is All Power Labs, as you've seen. And the location of the projects have been one in Opit, another one is in Muduma, and also we have together with the Pamojas installed and worked on some of those, as I mentioned before. So our experience, we have interfaced with gasification technologies that can support microgrid network. And also another project was SICK. We were looking at can we use the fecal matter or the fecal sludge that is abundant in most of the peri-urban to convert it into power. So we also tested that in the gasifier to see if it can generate electricity. So we are trying to look at diversifying the feedstock so that, of course, yes, it can support microgrid within even the peri-urban centers. So our experience has also shown us that, yes, there are different feedstocks such as maize, cobs, nutshells, coffee husk, and wood chips that we have interfaced. But mainly we started with the All Power Lab technology, which is we used that in the field. It worked very well. However, the challenge was, it's a 10 kilowatt system, and we were mainly using maize cob. And yes, we tried to compare even the performance of different feedstock. For example, if you see the maize cobs and wood chips in terms of their temperature at the bed and temperature at the reactor, you see that there is no much variation. However, the variation in performance comes in the pressure. There's P-com, there's P-react, there's P-filter. This is the pressure in the combustion chamber, pressure in the reactor, and pressure in the filter. You see the pressure is dropping so much in the filter because there is no much gas coming, or the gas coming when you're using wood chips is slow and creating negative pressure in the filter because of the packaging. The wood chips tend to package itself in the reactor, so the rate at which it generates is not as equal. It's not equal to maize cob that are, of course, all these parameters comes to what size did you use to do that. But we have at CREEK, we have also done comparison of feedstock performance. Yes, our experience, I've seen that we have experienced a lot of problems, especially with the tar that tend to block most of the blowers. We also have dust that comes in the different components, as well as clinkers developing when you burn it at a higher temperature, especially 1,200. So you have to take precaution. And our experience has also shown that there is potential impact where in Opit there were 30,000 farmers. And out of the 30,000 farmers, there were about 760 male with about 2,500 female, and also 9 institutions that we are serving with that 10 kilowatt. And most of the crops that were, The activities were related to milling rice, grinding maize, for food and for economic, like for selling. So our experience has also taught us that it is a very good venture for waste management through, since it adds value, it also creates community involvement and therefore resource, they will also try to manage the resource adequately. And being renewable in nature, you see, it does not pollute the environment, and it also provides energy security since they don't have to wait for fuel from another source to grind them. As well as we reduce emissions since we're using the gas for running in the engine, and there's less emission. We are talking about greenhouse gas emission. And therefore, economically, of course, that if you were to buy the other oil power lab, we bought it at $26,000. That's about $2,600 per kilowatt, which is slightly on a higher note. But when you're using the Ankoro, which is an Indian technology, it was the cost is about $2,000 per kilowatt. And of course, because of economy of scale, if you go beyond 100 kilowatt, it will drop to or below 1,500 kilowatt hour. Of course, the challenge is mainly about the operating and the maintenance cost, which sometimes because of the car, depending on the feedstock we are using, it will require you to frequently do services that may become costly. That is some of the on your far left is the oil power lab gas fire. On your right, it is the equipment we are using to operate. That is a maize sheller. So I can say that microgrid, biomass resources in Uganda can support microgrid, and it is evident that microgrid can change people's life. Thank you so much for listening to me.
Thank you. Thank you, Opio. Very interesting talk and very practical. I think that's something we really appreciate because I think those hands-on experience on operating a real gasifier, what sort of challenges, and also give us a very detailed overview of Uganda's resources and those potential projects and the future projects. That's really useful. And so our next speaker will be Francis Olanrewaju. He is a PhD project in the School of Chemical and Process Engineering at Leeds University. So his research project is looking at integrated utilization of sweet sorghum from Nigeria and how that can be used to produce energy in a way of you can use this solid waste for the gas fire. Then you also from sweet sorghum you can produce ethanol to potentially use for diesel engine. So that his case here, he wants to present us a case study for Nigeria. Okay, thank you.
Good day all, my name is Francis Omotola Olanrewaju, and the title of my presentation for the workshop is Sweet Sorghum as a Source of Renewable Energy for Electricity Generation, a Case for Nigeria. The presentation outline is as follows. The aim of the work was to investigate the syngas potential of sweet sorghum stalk residue by the restricted ventilation cone calorimeter technique. The objectives of this investigation were as follows. Firstly, to determine the yield of combustible gases, that is carbon monoxide, hydrogen, and total hydrocarbons from the gasification of sweet sorghum stalk residue. Secondly, to determine the optimum equivalent ratio phi and the hot gases efficiency of the gasification of sweet sorghum stalks. And last but not the least, to design a suitable gasifier for the investigated biomass based on the experimental results. Nigeria's annual biomass potential is estimated at 200 million tons. Nigeria is the third largest producer of sweet sorghum in the world. Gaseous renewable fuel, that is syngas, and liquid biofuel, that is bioethanol, can both be produced from sweet sorghum crop. The syngas can be produced from the stock residue of sweet sorghum by gasification. Bioethanol, on the other hand, can be produced from the grain, the juice, and the stock residue of sweet sorghum as depicted in Figure 1. Syngas and bioethanol can be used in diesel gensets for electricity generation by port injection of the syngas with direct injection of diesel bioethanol blend. Crop residues such as the stalks of sorghum and corn are usually set ablaze by farmers in Nigeria preparatory to the next planting season. This practice leads to enormous wastage of energy as well as environmental pollution. In this work, the syngas potential of sweet sorghum stock for electricity generation was investigated using the restricted ventilation cone calorimeter method. The stages involved in the investigation were depicted in Figure 2. First and foremost, the samples for the test were prepared by cutting the sweet sorghum stalks into 100 millimeter length. Thereafter, the test was run on the cone calorimeter rig. And thirdly, after the tests were conducted, the yield of the emitted gases as well as the optimum gasification equivalent ratio were determined. And last but not the least, a preliminary design of the biomass gasifier was done using computer-aided design package. The test conditions for the test were as depicted in Table 1. Basically, the gasification of the stock residues were carried out at 7 airflow conditions as shown in the second column of Table 1, and the equivalent air-free ratios for the tested conditions as well as equivalent ratios were as depicted in Table 1 in columns 3 and 4. The yield of the emitted gases were estimated from equation 1, whereas the hot gases efficiency HGE for the tested conditions were estimated using equation 2. The test rig is as shown pictorially in Figure 3. Starting from the right-hand side is a cone calorimeter itself, and the box just adjacent to the black line, which is the heated line, is the restricted ventilation system. It shows that air was passed into the box at metered rates, specifically chosen for the test. And then the first box on the table, starting from the right, is the FTR pump, and next to it is a FTR analyzer and the computer, the software, CalSmet software. And then the next monitor after the FTIR system is the ConeCalc software and computer linked to the cone calorimeter system. And underneath the black box there is a portable oxygen analyzer. Figure 4 shows the result for the yield of the emitted gases from the gasification of the sweet sorghum stalks residue. Figure 4 is a plot of the yield of the gases expressed as grams gas per kilogram biomass plotted against the equivalent ratio. Figure 5 underneath depicts the same plot, but this time around in terms of flow rate of the emitted gases against the equivalent ratio. The peak can be observed in the figure. The peak yield of gases as well as the peak flow rate were observed to have occurred at an equivalence ratio of 2.1. We also have inset views of the sweet sorghum stalks in the sample holder just prior to the gasification test, and the other view below shows the steady state flaming combustion during the test. The cone heaters can also be seen in the figure. Figure 6 shows the plot of the hot gases efficiency against the equivalence ratio. And on figure 6 it was also observed that the peak HGE occurred at an equivalence ratio of 2.1. The estimated optimum gasification equivalence ratio 5 for the gasification of sweet sorghum stock was 2.1, equivalent to an air flux of 12.9 grams per meter square per second. The estimated hot gases efficiency for the gasification of sweet sorghum stock biomass at the optimum condition was 89%. The HGE reported in literature is 80 to 90%. Hence, the estimated HGE for the gasification of sweet sorghum stock residue in this work falls within the range of HVE, Biomass HGE, that is given in literature. Preliminary design of the biomass gasifier. Table 2 shows the design specifications and constraints that were used to carry out the preliminary design of the gasifier for the investigated biomass. So the gasifier type chosen was natural downdraft fixed bed, because the test itself that was conducted was done in such a way as to mimic a fixed bed gasifier with the samples arranged in the sample holder and air introduced by downdraft. Natural downdraft air introduction has been chosen deliberately in this work in order to prevent entrainment of tar, as well as reduce entrainment of particulates, which conditions typically happen when an updraft air introduction design is used. The typical power rating for GenSet in Nigeria in kilowatt is 6.0. The gasifier is designed for a duration of operation of 12 hours per day, which time is sufficient for households, typically in the localities targeted in Nigeria, to freeze their perishable products as well as have some cooling in the house. The estimated air flux for the gasifier, based on the experimental results, was 12.9 meters square per second, and then the estimated syngas exit pipe diameter is 0.055 meters. The estimated capacity of the gasifier, based on these constraints, is 120 kilogram biomass per day. And the proposed design is as depicted pictorially in figure 7. Figure 7 shows a downdraft gasifier of capacity of 120 kg biomass per day, and basically the feed compartment is perforated as shown by the arrows in the figure, so that as the gasification occurs and the biomass is burned to ashes, the ashes would drop through the perforation into the ash hopper and exit through the ash dot as shown by the arrow. Air flow into the feed compartment, on the other hand, is through the adjustable air intake. Air flows basically upward into the air intake and then downward into the feed compartment where gasification will be occurring, whereas the emitted gases will rise up the gasifier, then through the syngas exit pipe and piped to a 6 kilowatt dual fuel reactivity controlled compression ignition mode GenSet. An RCCI mode GenSet has been chosen in this work because the certain number of syngas is relatively low compared to certain number of diesel, which means if syngas alone is used in the GenSet, there will be a problem of auto ignition. Hence, with port injection of syngas together with air into the cylinder of the GenSet, while DE diesel ethanol blend fuel is injected normally by direct injection, the charge can then auto-ignite, and so the engine will be able to run on the dual fuel, that is the fossil diesel injected by direct injection, already splash blend with bioethanol, as well as the syngas that will be introduced via port fuel injection. It's already been found and ascertained that the limit of solubility of bioethanol in fossil diesel is 20%. So with this scheme, electricity can possibly be generated using an RCCI mode GenSet from syngas obtained by the rich combustion of sweet sorghum biomass residue. The technique can also possibly be extended for microgrid electricity generation. In conclusion, the estimated optimum equivalent ratio phi and air flux for the gasification of sweet sorghum stock residue were 2.1 and 12.9 grams per meter squared second respectively. The hot gases efficiency of the product gases at the optimum equivalent ratio was 89%, which value falls within the range that's been reported in literature, the range of 80% to 90%. The current work has also shown that the syngas produced from the gasification of biomass residues can be used to generate electricity from a dual fuel genset operated in RCCI mode. And there's that acknowledgement. Thank you.
Thank you, Francis. And again, another very nice talk. I would have to say, Francis, you provided highly technical presentation and element. Excellent. You have a talk about this detailed combustion, detailed design requirement. That's also, I think, relevant to today's other talks. Thanks, Francis. So our next speaker is Dr. Andrew Ross. You already know him from a screen earlier in today's introduction and welcome session. So I just probably briefly mention a little bit about his bio, very brief. Dr. Andrew Ross is an associate professor in the School of Chemical and Process Engineering. His research interests cover a wide area from bioenergy, algae, biotechnology, waste to energy and nutrient recovery, etc. But his research interest mainly now is, I think, focused now on the integration of between thermochemical and biological conversion. Andy has been involved in all this international projects at Leeds and is the PI for the Biofuel project. So Andy, of course, the screen is yours now.
So my name is Andy Ross from the University of Leeds. I work on the CRESUM HYRES project, and I'd like to present some collaborative work that we've been doing with Dr. Gaurav Nahar from an Indian company called Defiant Renewables, and we've been looking at the potential for anaerobic digestion for power generation in microgrids, and in particular looking at a comparison of a range of different biomass feedstocks. So this is a collaboration between two projects, the CRESUM HYRES project and another GCRF funded project called Biofuel, which involves the utilisation of invasive aquatic biomass for the cleaning of water, for the production of biogas, for cooking, and the production of organic fertilizers. And so this presentation is going to do a number of back-of-an-envelope calculations to look at the yields and scenarios of using a number of feedstocks in India, and it's asking the question, is AD a serious contender for power generation in microgrids? So the questions that this presentation raises are, what are the biomass sources that could be used? How much biogas could they generate based on realistic production rates? How much power could they contribute to a microgrid? And then finally, how does it compare to solar PV? And so this will have an Indian perspective because Defiant Renewables are an Indian company. So the first question is, what type of biomass can we use? And so from an Indian perspective, there are many different types of biomasses, but in this presentation we've included cow dung, food waste, aquatic biomass, in particular water hyacinth, and human fecal matter. So we then considered the availability of the different feedstocks. So for the animal waste and the food waste, we've made an assumption of the amounts that are produced per person or per cow per day, and for the aquatic biomass, we've determined the amounts that can be harvested per metre squared per day. Now some of these biomass are available all year round, such as cow manure, food waste and fecal matter, and some of them are seasonal. So the water hyacinth presence is dependent upon the water body, where it's grown, and the type of water body. So typically we get about 20 to 30 kilos of cow dung per cow per day on a wet weight basis. We typically produce about 0.2 to 0.5 kilograms of food waste per person per day on a wet basis, and we typically produce about 0.25 kilograms of fecal matter per person per day on a wet basis. So for water hyacinth, we typically get about 0.5 kilograms per square metre per day on a wet weight basis. So what we've then done is use some back of an envelope calculations to determine how much biogas could be generated from these different feedstocks based on realistic production rates. So we've used a combination of BMP data with the composition of the biomass, for instance the ash and the moisture content, to predict how much biogas in litres per kilogram of feed we would get from the different feedstocks. And we've made the assumption that the biogas contains 50-50 methane to CO2. So we then ask the question, well, how much power could be produced from these different feedstocks and contribute to a microgrid? And we've based the scenario around a village containing about 1,000 people. Every 4 people or every family in the village owns 1 cow. So that produces about 160 cows, of which 25 to 50% of that cow dung is diverted into the digester. And that is then co-digested with some food waste and some fecal matter from the village, and also some water hyacinth that's been harvested from a local pond. And so we've included 3 scenarios where we've taken water hyacinth grown at different scales in either a small pond of 100 metres squared, a medium pond of 500 metres squared, or a larger pond at 1,000 metres squared. So this produces 50, 250 and 500 kilograms of biomass per day respectively. So this is our first scenario. So this is based on 25% of that dung in that village from those 160 cows being available and fed with 200 grams per day of food waste and 250 grams per day of fecal matter. And we've added to this 50 kilograms of water hyacinth, so that's associated with a 100 metre squared pond containing water hyacinth at 0.5 kilograms per day. So this result shows us quite a lot of information. So we have the bars is the amount of waste that is fed into the digester. The dotted lines are the amount of biogas that's produced from the different feedstocks, and the blue line is the amount of power that's generated from that biogas. So firstly, we can see that about 10% of the biogas is generated from the combination of food and fecal matter. So it does produce a significant amount. And on the x-axis, we've shown the different percentage of food and fecal matter collection. So we can increase this quite significantly if we go from 50% to 100% collection of food waste and fecal matter. If we look at the lowest power yield, so using 50% of the waste, food and fecal matter, we generate around about 3.4, and that equates to about 81 kilowatt hours per day. So this is our second scenario, again using 25% of the cow dung that's available. We're now increasing the amount of water hyacinth using a 500 meter squared medium-sized pond. That represents about 250 kilograms per day of water hyacinth. We now see that the water hyacinth alone produces about 10% of the biogas. And this results in a slight increase in the amount of power that's generated, even at 50% waste collection, so around about 3.7 kilowatt hours, and this represents about 89 kilowatt hours per day. So if we now look at the third scenario, where we have an even larger pond, 1,000 meters squared, which produces about 500 kilo of water hyacinth per day, we now see that the amount of biogas that's generated from water hyacinth alone increases to about 20%, and this represents an increase of power generation up to about 4 kilowatt hours, and that represents about 96 kilowatt hours per day. So while the water hyacinth and the food waste and the fecal matter make a significant contribution to the digester and the production of biogas, what is very clear is that the majority of the biogas is generated from the cow dung. And we can see this even more clearly if we increase the amount of cow dung from 25% collection to 50% collection. And this is shown on the next slide. So this figure now shows two blue lines. The bottom blue line is the power that's generated with 25% cow dung, and the top blue line is the collection of 50% cow dung. So we can see that the power that's generated, the biogas that's generated, is completely dominated by the amount of cow dung that's added. It has by far the largest potential to biogas production. And if we look at this 50% cow dung availability, then we get an increase in power up to between about 6 and 6.5, and this equates to about 144 kilowatt hours per day. So what we then tried to do was to make a comparison of the biogas system to solar PV. So we took a 10 kilowatt solar PV installation, and that produces around about 13,500 kilowatt hours per year in India, and that works out at about 30 to 40 kilowatt hours per day. And of course that's only available for 6 or 7 hours during the day. This equates to around about 5 kilowatt hours per hour of power, so it's not that dissimilar from the amount that's generated from the biogas plant. So the cost of a 10 kilowatt solar PV installation is about 400,000 rupees. So divided by 13,500 kilowatt hours per year, multiplied by a amortization factor of 0.1 over 10 years, and this works out at a generation cost of around 3 rupees per kilowatt hour. So then we do the same for the biogas plant. So we've assumed a 10 meter cube biogas plant produces between about 4 to 6 kilowatt hours per hour continually for 24 hours. So we've taken the lower value of 4 kilowatt hours. So the estimated cost is around about 1 million rupees, and it produces around 30,000 kilowatt hours per year. So again, multiplied by 0.1, the amortization factor, and that gives a generation cost of electricity of about 3.3 rupees per kilowatt hour. So they're very comparable in terms of cost when you just consider the kind of capital investment. Now if your cow dung is free, or your villagers supply it free, or you live on or you have a dairy farm that supplies cow dung at very low cost, then it looks quite good. But of course, in reality, the cow dung isn't free. And cow dung costs around about 2 rupees per kilogram typically, and biomass costs around 3 rupees per kilogram. And of course, we can sell the fertilizer as a digestate and make some money back, but it's unlikely that we'll make it all back. And if we factor this cost in of the feedstock, then even at a 2 rupees per kilogram cost of the dung, that increases the cost of the power generation up to around 15 to 20 rupees per kilowatt hour. So it's now more than the cost of regular grid power. So solar PV and biogas costs are comparable, but only if the cow dung is supplied at very low cost, or even supplied free. So if the cow dung costs any more than about 2 to 3 rupees per kilo, then the cost of generation becomes prohibitively high. On the plus side, anaerobic digestion does have some advantages. It can generate power all day, and you can store the biogas and then generate power at high demand using a biogas balloon. Now, there's also potential for integration of solar PV and anaerobic digestion. So for instance, if demand is low during the day, then the power that's generated from solar PV can be used to integrate with AD to improve AD operation. So one potential integration strategy would be to use the power generated during the day from solar PV when demand is low and it's not being used to produce hydrogen using electrolysis, and then to feed that hydrogen into an anaerobic digester to promote something called in situ biomethanation. And this converts hydrogen and CO2 into more methane, increasing the methane content of the biogas to as high as 90%. So this then produces more power, and this is a potential way of storing solar energy. Well, finally, some conclusions from the presentation. So in terms of India, one of the most important feedstocks is cow dung or cow manure. But if we want to produce power from a cow dung supplied anaerobic digestion unit, we really need to have a captive supply of dung, and it needs to be available at very low cost. So secondly, the use of water hyacinth as an alternative feedstock has great potential. It's a prolific generator of biogas. It represents a new supply chain for small-scale anaerobic digestion. The co-digestion of food wastes and fecal matter can make a significant contribution to biogas production, so it should be considered. And finally, anaerobic digestion has significant potential for energy storage, particularly on a small scale, and there's potential for innovation if integrated with solar PV. So I think therefore it can be said that anaerobic digestion does, under the right conditions, have significant potential for contributing to power generation of microgrids.